Subscribe so you don't miss out on any of these videos. Imagine a moon hidden in the vastness of space, its mysteries untouched by most of humanity's curiosity. While moons like Europa and Titan steal the spotlight, there are others, like Himalia, Hyperion, and Nereid, drifting quietly in the shadows. What secrets do these forgotten moons hold about the birth of our solar system? Join us as we uncover the untold stories of these elusive celestial bodies. Of all the celestial mysteries that linger in the vastness of our solar system, few are as overlooked as the forgotten moons. While names like Europa, Titan, and Enceladus dominate discussions of extraterrestrial exploration, a host of lesser-known moons drift silently in the gravitational embrace of their planetary hosts, each one harboring its own secrets, unique landscapes, and potential for unlocking the deeper mysteries of our cosmic neighborhood. These moons, often dismissed as minor celestial bodies, challenge our understanding of planetary formation, geologic activity, and even the potential for life beyond Earth. Among them, moons such as Himalia, Hyperion, and Nereid remain shrouded in obscurity, yet their stories are anything but insignificant. These forgotten worlds beckon us to explore their enigmatic surfaces, their strange orbits, and the unanswered questions they present. Questions that could reshape our comprehension of the solar system's history and the broader mechanics of the cosmos. Himalia, one of Jupiter's many moons, is a peculiar outlier in the gas giant's gravitational domain. Unlike the famous Galilean moons, which have been the focal point of extensive study and exploration, Himalia exists in a more remote and mysterious realm. Discovered in 1904 by astronomer Charles Dillon Perrine, Himalia orbits Jupiter at a significant distance, far beyond the main gravitational influence of the planet's larger moons. With an irregular shape and a surface that appears to be composed of water, ice, and rock, Himalia is believed to be a captured asteroid or perhaps even the remnant of a once larger celestial body that succumbed to Jupiter's immense gravitational pull. Its surface, largely unobserved due to its small size and distance from Earth, is thought to be battered by countless eons of cosmic impacts, leaving behind an ancient, cratered landscape that has remained unchanged for billions of years. Unlike Europa or Ganymede, which exhibit clear signs of geologic activity, Himalia is a silent, frozen relic of the early solar system. Yet its very existence raises questions: how did it come to be in Jupiter's orbit? Was it once part of a larger body, shattered by gravitational disruptions? Could it harbor clues about the formation of the gas giant's sprawling system of moons? Hyperion, on the other hand, presents an entirely different enigma. As one of Saturn's more bizarre satellites, Hyperion defies expectations in nearly every way. Unlike most moons, which tend to settle into relatively stable, predictable rotations, Hyperion tumbles chaotically through space, its motion erratic and seemingly random. This strange behavior is a result of its highly irregular shape and its gravitational interactions with the much larger Titan. Unlike the smooth, icy surfaces of Enceladus or Rhea, Hyperion's exterior is pockmarked with deep, sponge-like craters, giving it a porous and eerily organic appearance. Scientists believe that Hyperion is not dense enough to be a solid object in the traditional sense. Instead, it may be a loosely bound aggregation of rock and ice, its porous nature making it more akin to a cosmic snowball than a typical moon. Its low density suggests that much of its internal structure is empty space, a characteristic that makes Hyperion one of the least understood objects in Saturn's orbit. What is particularly intriguing about Hyperion, however, is its electrical interactions with Saturn's magnetosphere. When Cassini flew past Hyperion, the spacecraft detected unexpected electrostatic charges on the moon's surface, raising questions about the role of electromagnetic forces in the Saturnian system. Could Hyperion's chaotic motion and strange structure hint at broader, yet undiscovered processes shaping Saturn's moons? Could its bizarre surface composition be a result of interactions with Saturn's powerful radiation belts? These are the mysteries that make Hyperion an object of deep scientific curiosity. Even farther from the Sun, Nereid orbits Neptune in a manner that defies conventional expectations. Nereid's orbit is one of the most eccentric in the solar system. Rather than following a relatively circular path around its planet, Nereid swings wildly between extreme distances, sometimes approaching Neptune closely, only to drift far into the outer reaches of its gravitational domain. This erratic motion suggests a violent past, possibly the result of an ancient collision or gravitational interaction that disrupted what was once a more stable orbit. Discovered in 1949 by Gerard Kuiper, Nereid remains one of Neptune's most mysterious moons, largely because it has been studied only briefly and at great distances. Voyager 2 provided the only close-up images of Nereid during its 1989 flyby, and even those were limited in detail. What little is known suggests that Nereid is composed primarily of ice and rock, with a surface that has likely been shaped by eons of impact events. Theories about its origins suggest that it may have once been a Kuiper belt object, captured by Neptune's gravity in a distant epoch. If this is the case, then Nereid serves as a vital link between the worlds of the inner solar system and the icy, uncharted frontier beyond Neptune. Could it be a time capsule, preserving materials from the early days of the solar system? Could its erratic orbit reveal hidden gravitational influences, perhaps even hinting at undiscovered moons or planetary interactions in the Neptunian system? These forgotten moons are not mere footnotes in the grand story of our solar system. They are critical pieces of a larger puzzle, each one offering a unique perspective on planetary formation, gravitational interactions, and the complex web of forces that have shaped our cosmic neighborhood. Himalia, Hyperion, and Nereid represent just a fraction of the many moons that remain unexplored and largely misunderstood. The more we learn about these distant, enigmatic worlds, the more we realize how little we truly understand about the intricate dance of celestial bodies that defines our solar system. As future missions extend our reach beyond the familiar, these forgotten moons may yet yield some of the most astonishing discoveries of all. Insights that could challenge our assumptions about planetary evolution, the mechanics of chaotic motion, and even the possibility of life in the most unexpected places. Their isolation, their peculiarities, and their very existence remind us that the mysteries of space are far from solved. Their isolation, their peculiarities, and their very existence remind us that the mysteries of space are far from solved. Each of these moons, Himalia, Hyperion, and Nereid, presents a set of unique questions that could redefine what we know about the solar system. And they are not alone. The deeper we look, the more we realize that the solar system is filled with moons that exist in the margins of planetary science, waiting to be explored, waiting to reveal secrets hidden in their icy crusts, rugged surfaces, or chaotic orbits. Take, for example, Sycorax, a distant moon of Uranus that follows an unusually elongated, retrograde orbit. Unlike the well-known major moons of Uranus, Miranda, Ariel, Umbriel, Titania, and Oberon, Sycorax is an outlier, both in terms of its location and its behavior. It resides in the farthest reaches of Uranus's gravitational influence, so distant that it likely never formed alongside the planet. Instead, astronomers suspect that Sycorax was captured from the Kuiper belt, an icy region beyond Neptune that contains remnants from the early solar system. If true, Sycorax is a time capsule of cosmic history, potentially preserving material that has remained unchanged for billions of years. But its extreme distance makes it difficult to study, leaving its true nature largely speculative. Does it have an active surface? Could it be hiding a subsurface ocean like Europa or Enceladus? Or is it a dead world, an ancient relic adrift in the cold void? Then there's Phoebe, an unusual satellite of Saturn that defies easy classification. Unlike most of Saturn's moons, which formed from the same disk of material that gave birth to the planet itself, Phoebe appears to be something entirely different, an outsider. It orbits in a retrograde motion, meaning it moves in the opposite direction of Saturn's rotation, which is a strong indication that it was captured long ago from the outer solar system. Scientists believe Phoebe may have originated in the Kuiper belt, much like Pluto and other icy objects that populate the distant frontier of our planetary neighborhood. Unlike Hyperion's sponge-like surface or Titan's thick atmosphere, Phoebe's surface is dark and ancient, covered in craters that suggest it has remained geologically inactive for eons. However, data from the Cassini spacecraft revealed that Phoebe is composed of a mix of ice and rock, suggesting that it could be a primordial object, perhaps one of the earliest building blocks of the solar system. Could studying Phoebe provide insight into how planets and moons originally formed? What can it tell us about the migration of celestial bodies across the solar system? If Phoebe is a captured Kuiper Belt object, it may contain the very ingredients that shaped the early Earth and possibly even the conditions necessary for life. Beyond Saturn, Neptune harbors another enigmatic moon, Proteus. Unlike its eccentric sibling Nereid, Proteus follows a more conventional orbit around Neptune, yet its sheer existence is puzzling. Proteus is incredibly dark, reflecting very little sunlight, making it difficult to observe even with powerful telescopes. It is also oddly shaped, more akin to an asteroid than a moon, which suggests that it lacks the gravitational strength to pull itself into a perfect sphere. Scientists believe that Proteus may have once been part of a larger body that was shattered by a violent impact, leaving behind a lumpy, irregular remnant. This idea raises an intriguing question. If Proteus is a fragment of a once larger moon, what happened to the rest of it? Could Neptune's immense gravitational influence have played a role in its destruction? And if such an event occurred, could there be more missing pieces of Neptune's ancient history waiting to be discovered? Even Pluto, once considered the 9th planet of our solar system, has a moon system that defies expectations. While Charon, the largest of Pluto's moons, is well known for its gravitational interactions with its parent body, Pluto's smaller moons, Styx, Nix, Kerberos, and Hydra, exhibit bizarre rotational behaviors that remain unexplained. Unlike most moons, which maintain a relatively stable spin as they orbit their planets, Pluto's smaller moons tumble unpredictably, as if they are being influenced by unseen forces. Scientists speculate that this chaotic motion is the result of Pluto and Charon's unusual relationship. Since Charon is so large compared to Pluto, the two bodies effectively orbit a common center of mass rather than Pluto alone. This gravitational quirk disrupts the stability of the smaller moons, leading to their erratic tumbling. Could this strange motion tell us something fundamental about how binary planetary systems function? And if Pluto's moons are this unpredictable, what does that mean for similar systems elsewhere in the galaxy? As we venture farther into the solar system, we encounter even more strange and forgotten moons, each one presenting a new set of mysteries. Triton, Neptune's largest moon, is an oddity in every sense of the word. It orbits Neptune in the opposite direction of the planet's rotation, making it one of the few large moons in the solar system with a retrograde orbit. This suggests that Triton was not originally a moon of Neptune at all. It was likely captured from the Kuiper Belt long ago. Triton's surface is also uniquely active, featuring cryovolcanoes that spew liquid nitrogen into space, creating a thin atmosphere that waxes and wanes as the moon moves through its orbit. This raises a compelling possibility. Could Triton still possess internal heat, despite its extreme distance from the sun? If so, what drives its geologic activity? Could subsurface oceans lurk beneath its frozen crust, providing a potential habitat for microbial life? The forgotten moons of the solar system are more than just distant, icy rocks. They are keys to understanding the forces that shaped our cosmic neighborhood, relics of a past that predates even the formation of Earth. These moons challenge our assumptions about how celestial bodies interact, how planets acquire their satellites, and even how life might arise in the most unexpected corners of space. Every one of these forgotten worlds holds the potential for groundbreaking discoveries, whether it be through future space probes, advanced telescopes, or the theoretical models that seek to explain their origins and behaviors. They may be distant and often overlooked, but they are not insignificant. They are waiting in the cold darkness of space to tell us their stories. And when we finally listen, we may find answers to some of the most profound questions about the nature of our universe. The forgotten moons of the solar system remain some of the most intriguing and underexplored celestial bodies in our cosmic neighborhood. While major moons like Europa, Titan, and Enceladus captivate scientists with their potential for life and active geology, the smaller, more obscure moons orbiting planets like Jupiter, Saturn, Uranus, and Neptune hold just as many secrets, if not more. These moons are often irregular in shape, chaotic in motion, and puzzling in composition, hinting at violent pasts, ancient collisions, and the lingering gravitational forces that continue to shape them. Understanding them is crucial to piecing together the larger story of the solar system's formation, its evolution, and the forces that govern the movement of celestial bodies across time. One such enigmatic world is Ananke, a tiny and distant moon of Jupiter that follows a retrograde orbit. Discovered in 1951 by astronomer Seth Barnes-Nicholson, Ananke is part of a group of irregular moons that move in the opposite direction of Jupiter's rotation. This suggests that Ananke was not originally formed within Jupiter's system but was instead a captured asteroid or a fragment of a larger body that broke apart due to a collision. What makes Ananke particularly fascinating is its possible role in the formation of Jupiter's outer moons. Scientists believe that several other small moons in Jupiter's orbit may be pieces of Ananke, remnants of a violent impact that shattered a parent body billions of years ago. If true, studying Ananke and its counterparts could provide invaluable information about the chaotic environment of the early solar system, when planetary formation was still in progress and massive collisions were far more common. Moving further out, we encounter yet another mysterious world, Albiorix, an irregular moon of Saturn. Albiorix is part of the Gallic group, a cluster of Saturnian moons that share similar orbital characteristics, suggesting that they may have originated from a single larger body that was torn apart. What makes Albiorix stand out, however, is its unusual reddish coloration, which differs from the icy white and gray tones seen on many other moons in Saturn's orbit. This distinct color suggests that Albiorix may have been exposed to different space weathering processes or that it contains a unique composition of materials not commonly found elsewhere in the Saturnian system. Could Albiorix be hiding remnants of an ancient object from the outer solar system? Could its surface composition hold clues about the chemical interactions that occur in deep space? Beyond Saturn, Uranus's moon Caliban presents another perplexing mystery. Like many of the planet's outer moons, Caliban follows a highly inclined and retrograde orbit, suggesting that it was a captured object rather than one that formed alongside Uranus. Discovered in 1997, Caliban is one of the least studied moons in the solar system. No spacecraft has ever visited it, and even high-powered telescopes struggle to reveal much about its surface features or composition. What little we do know suggests that it is composed of a mix of rock and ice, much like other irregular moons in the outer solar system. However, its true origins remain uncertain. Did it originate in the Kuiper Belt? Was it once part of a larger body that disintegrated? Could it have been influenced by gravitational interactions with Neptune before settling into its current orbit around Uranus? Then there is Larissa, a moon of Neptune that exists in an environment filled with gravitational chaos. Unlike its erratic sibling Nereid, Larissa orbits much closer to Neptune, residing just inside the planet's faint ring system. First discovered in 1981 by astronomers analyzing data from ground-based telescopes, Larissa was later confirmed by Voyager 2 during its historic 1989 flyby of Neptune. What makes Larissa so intriguing is the fact that it appears to be slowly drifting inward toward Neptune, its fate potentially sealed by the relentless pull of the planet's gravity. If this trend continues, Larissa may one day spiral too close to Neptune and be torn apart, possibly contributing to the planet's rings or forming a new generation of debris that could eventually coalesce into another moon. This process of tidal disruption and moon formation is still poorly understood, and studying moons like Larissa could provide insights into how planetary ring systems evolve over time. Even beyond Neptune, in the most distant reaches of the solar system, there exist moons that challenge our understanding of planetary dynamics. Take, for example, Dysnomia, the tiny moon of the dwarf planet Eris. Discovered in 2005, Dysnomia orbits Eris in a nearly circular path, raising questions about how it formed and what role it plays in the evolution of distant trans-Neptunian objects. Because Eris itself is one of the most massive known objects in the Kuiper Belt, studying Dysnomia could help scientists determine whether large dwarf planets frequently host moon systems and whether similar processes that shaped Pluto and Charon also influenced Eris and Dysnomia. The more we learn about these far-flung celestial bodies, the more we can infer about the conditions that existed in the early solar system when planet-sized objects were colliding, merging, and capturing one another in a gravitational ballet that continues to unfold even today. These moons, often overlooked and rarely discussed, each offer a unique piece of the puzzle that is our solar system's history. Some of them are remnants of violent pasts, shattered and reassembled through gravitational forces we still struggle to fully comprehend. Others are captured wanderers, pulled from distant regions of space into the orbits of giant planets where they now reside as cosmic refugees. Some are still active, their surfaces changing over time due to tidal heating, cosmic bombardment, or unknown internal processes. And some, like Triton, Hyperion, and Phoebe, continue to defy expectations, challenging our assumptions about what moons should be and what secrets they might hold. Yet despite their importance, these moons remain largely ignored by space agencies and scientific institutions. Missions to the outer solar system are rare, and when they do occur, they tend to focus on the most well-known and promising targets: Europa, Titan, and Enceladus. The forgotten moons remain just that, forgotten, their mysteries left unresolved due to lack of exploration and technological limitations. But with the rise of more advanced space telescopes, robotic probes, and even future crewed missions to deep space, there is hope that one day these neglected worlds will get the attention they deserve. What might we find if we were to send dedicated missions to study these moons up close? Could Himalia's surface reveal the scars of an ancient asteroid impact that reshaped Jupiter's moon system? Could Hyperion's chaotic motion be a clue to hidden gravitational forces at play in Saturn's orbit? Could Nereid's strange, elliptical path tell us something new about Neptune's interactions with the outer solar system? Every question unanswered is a door left open, a possibility waiting to be explored. The forgotten moons of the solar system are not mere background objects in the grand celestial dance of planets and stars. They are dynamic, evolving, and full of stories yet to be told. In their craters and ice-covered plains, in their irregular orbits and unusual compositions, they hold the key to understanding not just how the solar system came to be, but also where it is going. They are remnants of a time before Earth, before the sun shone its first light, before the planets took their final forms. They are survivors of a chaotic past, witnesses to the ever-changing nature of the universe. And they remind us that in the vastness of space, no world is too small to hold the answers to some of the biggest questions we have ever asked. If we could explore these forgotten moons in detail, the insights we might gain could change our understanding of planetary evolution and the forces that shape celestial bodies across billions of years. Consider, for example, the mysterious moon Himalia, one of Jupiter's largest irregular moons. Despite its relatively significant size compared to other outer moons, Himalia remains a mystery. It orbits far from Jupiter, in a region where captured asteroids and fragmented bodies from past collisions likely reside. Unlike the Galilean moons, which formed in Jupiter's early circumplanetary disk, Himalia is believed to be an interloper, an object that wandered too close to Jupiter and was snatched by its immense gravity. But how did it get there? Was Himalia once part of a larger body that was shattered, much like Encke's possible origin? Its relatively high albedo suggests that its surface may contain water ice, but it lacks the telltale signs of cryovolcanism or subsurface activity seen on moons like Europa. Some scientists speculate that Himalia may have once belonged to the Kuiper belt before being pulled inward, which would make it an invaluable relic from the outer solar system. Studying it up close could provide a direct look at the type of materials that existed in the early solar nebula. Could Himalia hold chemical signatures that predate Jupiter itself? Could it be the missing link between asteroid belt bodies and distant trans-Neptunian objects? Then there's Hyperion, one of Saturn's strangest moons. Unlike any other major moon in the solar system, Hyperion has an irregular, sponge-like appearance, with deep craters that seem to have been carved out by countless impacts over time. Its low density suggests that it is not a solid rock but rather a porous, icy body with a significant amount of empty space inside. This raises intriguing questions about its formation. Was Hyperion once part of a larger moon that was shattered? Could it be the remnant of a comet-like body that got trapped in Saturn's orbit? What's even more puzzling is Hyperion's chaotic rotation. Unlike most moons, which rotate predictably around their parent planets, Hyperion's motion is erratic and unpredictable, tumbling through space in a way that defies easy explanation. This suggests that it has been subjected to unusual gravitational interactions, possibly with Titan or other Saturnian moons. If we could land a probe on Hyperion, what might we find? Would its surface contain clues about its internal composition? Could its strange motion be explained by hidden subsurface structures or gravitational anomalies? Hyperion is a reminder that the solar system is still full of surprises, and that even well-known planets like Saturn have secrets waiting to be uncovered. Moving outward to Neptune, we find Nereid, a moon that behaves unlike any other in the outer solar system. Nereid's orbit is highly elliptical, meaning it swings from a relatively close distance to Neptune to an incredibly distant point, making it one of the most extreme orbits of any known moon. This erratic movement suggests that Nereid was either captured by Neptune's gravity from a distant region of space or that it was severely disturbed by an ancient gravitational event, perhaps the same one that led to Neptune's capture of Triton, its largest moon. If Triton was once a dwarf planet that was pulled into Neptune's orbit, the resulting disruption may have sent Nereid into its current chaotic path. But Nereid's true nature remains elusive. It is one of the largest known irregular moons, yet we have little more than grainy telescope images and distant observations from Voyager 2 to go on. Could Nereid be an ancient Kuiper belt object that has remained largely unchanged since the early days of the solar system? Does its surface contain primordial materials that have never been altered by geological processes? If we could study it in greater detail, we might learn more about the dynamics of Neptune's system and how giant planets interact with the objects that drift into their gravitational influence. Beyond Neptune, the mysteries continue with objects like Dysnomia, the small moon of the dwarf planet Eris. Dysnomia's existence suggests that even distant icy worlds can have their own complex histories. If Eris, like Pluto, underwent a collision that led to the formation of its moon, studying Dysnomia could reveal the nature of those ancient impacts. It could also help us determine whether binary or multi-moon systems are common in the Kuiper belt. Could Dysnomia's orbit provide clues about Eris's internal structure? Could the interaction between these two bodies shed light on how dwarf planets evolve over time? The farther we look into the forgotten corners of the solar system, the more we realize how much remains unexplored. Some of these moons could hold answers about planetary migration, the nature of ice-covered worlds, and even the possibility of life in extreme environments. What if some of these moons, despite their small size and irregular orbits, harbor hidden subsurface oceans, just like Europa or Enceladus? What if they contain organic molecules that hint at the building blocks of life beyond Earth? These are questions that we may never answer unless future space missions prioritize the study of these neglected worlds. In the coming decades, as space agencies develop more advanced telescopes, robotic explorers, and possibly even crewed missions to the outer solar system, we may finally begin to uncover the secrets of these forgotten moons. Probes equipped with spectrometers, radar imaging, and landers could revolutionize our understanding of these celestial bodies. Imagine a mission specifically designed to explore the irregular moons of Jupiter, Saturn, Uranus, and Neptune, a fleet of small, nimble spacecraft that could navigate the complex gravitational environments of these systems and provide unprecedented data. With new technologies like nuclear-powered spacecraft and next-generation propulsion systems, such a mission is not beyond the realm of possibility. As we expand our reach into the cosmos, the forgotten moons of the solar system remind us that the greatest discoveries may not come from the largest or most famous worlds, but from the small, overlooked objects that have quietly existed for billions of years. These moons are relics of a time when the solar system was a chaotic and violent place, when planets were still forming and gravitational forces were shaping the structure of our celestial neighborhood. Each crater, each orbit, each fragment of ice or rock tells a story, if only we take the time to listen. For now, these moons remain in the shadows, their mysteries hidden from view, waiting for the day when humanity finally turns its attention toward them. And when we do, who knows what we might find? The answers could redefine our understanding of the solar system and our place within it. The mysteries of these forgotten moons extend far beyond their isolated orbits and peculiar compositions. Each one is a frozen time capsule, preserving evidence of past collisions, gravitational disruptions, and even the raw materials that existed when the solar system was still forming. By studying them, we could piece together a clearer picture of how planetary systems evolve, how moons form and migrate, and whether conditions favorable for life might exist in places we've never considered. Take, for instance, the smaller, irregular moons of Uranus, such as Sycorax and Caliban. These moons, named after characters from Shakespeare's The Tempest, are barely studied, yet they hold clues about the chaotic history of the ice giant they orbit. Unlike Uranus's major moons, Miranda, Ariel, Umbriel, Titania, and Oberon, these smaller bodies follow retrograde orbits, meaning they move in the opposite direction of Uranus's rotation. This suggests that they were not formed alongside the planet but were likely captured from elsewhere, possibly from the Kuiper belt or even interstellar space. If we could analyze their surface compositions, we might be able to confirm whether they are remnants of a past planetary collision or if they originated in the distant reaches of the solar system. Another oddity among forgotten moons is Phoebe, an irregular moon of Saturn that stands out due to its retrograde orbit and extremely dark surface. Unlike the icy moons that dominate Saturn's system, Phoebe appears to be made of carbon-rich material, similar to objects from the outer solar system. In fact, some scientists believe that Phoebe may be a captured centaur, a type of small body that originates between the orbits of Jupiter and Neptune but occasionally migrates inward due to gravitational interactions. This would mean that Phoebe is an ancient relic, potentially as old as the solar system itself. One of Phoebe's most intriguing aspects is that it appears to have a surprisingly complex internal structure. Observations from NASA's Cassini spacecraft suggest that Phoebe may have once been spherical and experienced some degree of differentiation, meaning that heavier materials sank to its core while lighter materials remained on the surface. If true, this would indicate that Phoebe once had enough internal heat, possibly from radioactive decay, to partially melt and reshape itself. Could Phoebe be a failed moon, one that started to develop into a more complex body but never fully evolved? Could it contain trapped volatiles, such as ammonia or methane, that might hint at chemical processes occurring deep within? Moving back to Neptune, another strange moon demands attention: Proteus. Unlike Neptune's largest moon, Triton, which is believed to be a captured dwarf planet, Proteus is thought to have formed from the debris left behind after Neptune's chaotic early history. What makes Proteus particularly interesting is that it is one of the largest bodies in the solar system that is not spherical. At approximately 420 kilometers in diameter, it is right on the edge of having enough gravity to pull itself into a round shape, yet it remains irregular. This suggests that Proteus has experienced little to no internal heating, leaving it frozen in time as a remnant of Neptune's early evolution. However, there is something even stranger about Proteus. It has a massive impact crater, nearly large enough to have shattered the moon entirely. If the impact had been just slightly more powerful, Proteus might have been broken apart, adding to Neptune's already complex moon system. The presence of such a large crater suggests that Neptune's moons have been subjected to intense bombardment, possibly from leftover debris in the solar system's early days. Could Proteus be the survivor of a much larger moon that was destroyed in a collision? Could remnants of that ancient impact still be drifting somewhere in Neptune's gravitational influence? The deeper we look into the solar system, the more we realize that the moons we so often ignore may be among the most scientifically valuable. Even the smallest and least studied of these moons could provide crucial data on the movement of ice and rock in space, the frequency of cosmic collisions, and the hidden chemistry that might exist in their interiors. What if some of these moons contain frozen organic compounds, preserved from the earliest days of the solar system? Could they act as stepping stones for future missions, serving as refueling stations or research outposts for humanity's expansion beyond Earth? It is astonishing how little we know about the outer solar system compared to the inner planets. While Mars, Venus, and the Moon have been explored extensively, and even the gas giants have had dedicated missions like Galileo and Juno, the moons orbiting Neptune, Uranus, and even Saturn and Jupiter remain largely untouched. Voyager 2 provided humanity with our only close-up images of Uranus and Neptune's moons, and those images are now over 3 decades old. Since then, no mission has returned to study them in detail. What secrets might we uncover if we sent modern, high-resolution cameras and spectrometers to scan these forgotten worlds? Perhaps one of the most exciting possibilities is the potential discovery of active geology on some of these moons. While most are believed to be inactive, with ancient surfaces marked by craters, we have been surprised before. When the Voyager spacecraft first flew past Io, scientists were astonished to see towering volcanic plumes erupting into space. More recently, Enceladus shocked astronomers with its cryovolcanic jets of water ice, spewing material into Saturn's rings. Could there be similarly unexpected activity on moons like Sycorax, Proteus, or Nereid? Could they be venting gas, indicating hidden subsurface reservoirs of liquid? Could strange, unknown processes be shaping their surfaces even now? If we had the technology to visit these moons up close, we could analyze their surface materials, measure their magnetic fields, and search for evidence of past or present geological activity. A lander on a forgotten moon like Hyperion or Himalia could provide groundbreaking discoveries about the chemistry of these distant worlds. A sample return mission could tell us whether they contain organic molecules or isotopic signatures that hint at their origins. A fleet of orbiters around Neptune or Uranus could finally give us the data needed to understand these neglected regions of the solar system. The biggest challenge in studying these moons is the vast distance separating them from Earth. A mission to Neptune, for example, would take well over a decade to arrive, and any data it sends back would take hours to reach us. The extreme cold and harsh radiation environments make long-term exploration difficult. However, with the rapid advancements in artificial intelligence, autonomous navigation, and miniaturized scientific instruments, we are closer than ever to overcoming these obstacles. The upcoming missions to Jupiter's icy moons, such as the European Space Agency's JUICE mission and NASA's Europa Clipper, are already paving the way for advanced exploration techniques that could be applied to Neptune, Uranus, and beyond. For now, these forgotten moons remain little more than distant specks of light, their mysteries locked away in the cold depths of space. But as our technology improves and our curiosity drives us further into the cosmos, we may one day stand on the surface of these neglected worlds, looking out at the stars and wondering what other secrets the universe is waiting to reveal. The mysteries of these forgotten moons are not just limited to their pasts, they also hold potential clues about the future of planetary systems and even the fate of our own solar system. Each of these moons represents a unique snapshot of cosmic evolution, an untouched relic from a time when planets were still forming and the solar system was a chaotic place filled with collisions, migrations, and gravitational reshuffling. By studying these moons in greater detail, we might uncover secrets about how moons are captured, how planetary rings form, and whether similar processes occur in exoplanetary systems across the galaxy. Consider the case of Chloe, a tiny and irregularly shaped moon of Jupiter. It was once thought to be an asteroid, only to later be identified as one of Jupiter's many outer moons. What's fascinating about Chloe is that it follows a highly eccentric orbit, suggesting that it was likely captured from the Kuiper belt or the asteroid belt. If so, it could provide valuable information about how Jupiter, with its immense gravitational influence, continues to shape the solar system by pulling in and disrupting smaller objects. Could Chloe be a fragment of a once larger body that was shattered in a collision? Could it hold clues about the types of materials that existed in the early solar system? Another fascinating yet overlooked moon is Pasiphae, another irregular satellite of Jupiter. It is part of a group of retrograde moons, meaning it orbits in the opposite direction of Jupiter's rotation, suggesting that it was captured rather than formed alongside Jupiter. The presence of these retrograde moons raises a compelling question. Where did they come from? Did they originate in the outer solar system, or are they remnants of a moon that was torn apart by Jupiter's powerful gravitational forces? If so, could we still detect traces of that ancient destruction in the form of dust rings or other debris? Moving beyond Jupiter, the forgotten moons of Saturn also hold intriguing mysteries. While Titan and Enceladus receive much of the attention, moons like Iapetus and Hyperion remain largely unexplored. Hyperion, in particular, stands out because of its bizarre sponge-like appearance. Unlike most moons, which tend to be relatively smooth or cratered, Hyperion looks almost porous, as if it were filled with holes. Scientists believe this could be due to its extremely low density, which prevents impacts from compacting its surface the way they do on denser moons. But what if Hyperion's odd shape is due to something even stranger, an ancient collision that left it fractured and riddled with voids? Could its interior still hold pockets of trapped gas or ice? Iapetus, meanwhile, presents an entirely different puzzle. It is known for its dramatic color contrast. One side is bright as snow, while the other is as dark as coal. Theories suggest that this could be the result of material from another moon, Phoebe, slowly coating one hemisphere of Iapetus as it moves through space. But why does this contrast remain so sharp and distinct, rather than gradually blending together over time? Could Iapetus have some unknown geological process keeping this division intact? Could subsurface heating or outgassing be at play? Moving even farther out, the moons of Uranus remain some of the least studied in the entire solar system. While the major moons, Miranda, Ariel, Umbriel, Titania, and Oberon, have been observed in some detail, Uranus's smaller and more irregular moons, like Sycorax and Caliban, remain largely unknown. Given their odd orbits and compositions, they are thought to be captured objects rather than moons that formed alongside Uranus. But where did they come from? Were they part of the original Kuiper Belt population before being drawn into Uranus's orbit? If so, could they contain unaltered material from the early solar system, untouched by the heating and processing that affected objects closer to the Sun? The most tantalizing of all forgotten moons might be Triton, Neptune's largest moon. While not as obscure as some of the smaller irregular moons, Triton is still shrouded in mystery because it is the only large moon in the solar system that orbits in the opposite direction of its planet's rotation. This strongly suggests that Triton was not originally a moon of Neptune but was instead captured from the Kuiper Belt. If true, then Triton could be an analog to Pluto, a large icy world that was once independent before being pulled into Neptune's gravitational influence. This means that studying Triton up close could give us an unprecedented look at the types of objects that populate the distant Kuiper Belt and even help us understand how dwarf planets evolve over time. But what if Triton's capture event was more dramatic than we realize? Some scientists speculate that when Triton was pulled into Neptune's orbit, it may have disrupted Neptune's original moon system, causing other moons to either be ejected into space or collide with each other. If this happened, we might still be able to detect evidence of that ancient upheaval in the form of faint ring structures, debris fields, or even remnants of destroyed moons still lurking near Neptune. Nereid, one of Neptune's outer moons, also presents an intriguing mystery. Unlike Triton, which has a relatively stable retrograde orbit, Nereid follows one of the most eccentric orbits of any known moon in the solar system. At its closest, Nereid comes within 1.4 million kilometers of Neptune, but at its farthest, it drifts nearly 10 million kilometers away. This suggests that Nereid was once in a more stable orbit before being disturbed, perhaps by Triton's capture or by another massive gravitational event. If we could study Nereid's surface, we might find evidence of ancient tidal heating, which could tell us more about how Neptune's moon system has evolved over time. The question that lingers over all these forgotten moons is, what else are we missing? We have barely scratched the surface when it comes to understanding these distant worlds. Could some of these moons hold evidence of prebiotic chemistry, similar to what has been detected on Europa or Titan? Could some of them still be geologically active in ways we have yet to observe? Could they even contain hidden subsurface oceans, buried beneath thick layers of ice? Future missions will need to prioritize these forgotten moons if we truly want to understand the full complexity of our solar system. Proposals have been made for missions to Uranus and Neptune, but they remain in the early planning stages. If humanity ever hopes to push further into space, to establish colonies, to mine asteroids, or even to send humans beyond the outer planets, understanding these moons will be essential. They could provide natural stepping stones for future exploration, offering potential fuel sources, water reserves, or even hidden habitable environments. Until we send more probes, these moons will remain distant enigmas, tiny specks of light orbiting their parent planets in silence. But one day, a spacecraft may touch down on the surface of Nereid, drill into the ice of Iapetus, or fly through the dust trails of Sycorax. And when that day comes, we may finally uncover the incredible hidden stories of these forgotten worlds. As the years pass and technology advances, we are inching closer to answering the many mysteries surrounding these enigmatic moons. Future space missions will undoubtedly play a critical role in uncovering the secrets of these forgotten moons, potentially reshaping our understanding of planetary science and our place in the universe. But it's not just the exploration of distant moons that fascinates us. It's the quest to understand the history and processes that have shaped the solar system over billions of years. One of the most intriguing aspects of these forgotten moons is how they offer a window into the solar system's early days. For instance, Nereid's eccentric orbit, while currently an intriguing anomaly, may be a remnant of a chaotic early solar system. The gravitational disturbances caused by large planetary migrations, such as the supposed migration of Jupiter or Neptune, could have been responsible for the orbits of these moons. In this view, Nereid and moons like it could hold the key to understanding the massive shifts that once occurred in the outer solar system. Take, for example, the remarkable oddities of Saturn's moons, like Hyperion. Its highly irregular shape, described as resembling a sponge, is a significant point of interest. This oddity is perhaps the result of Hyperion's low density, so low that the moon is thought to have a porous structure. How such a porous moon formed and survived in the volatile environment of the outer solar system remains an unresolved question. Could it be that Hyperion is a fragment of a much larger moon that was shattered by a catastrophic event? Alternatively, might it have once been a much denser object that slowly lost its mass over billions of years due to a combination of gravitational forces and collisions? The moon's strange gravitational behavior and appearance suggest that Hyperion's history is filled with complex interactions, and studying it may help us understand more about the life cycle of moons and the impacts of planetary formation. We can also examine the case of Himalia, one of Jupiter's irregular moons. While it's relatively small compared to some of Jupiter's other moons, Himalia's orbit is incredibly interesting. It follows a retrograde orbit, which, like many of Jupiter's outer moons, suggests it was likely captured by the planet's gravity rather than forming in orbit with it. Himalia's surface is composed of icy materials, and its unusual orbit raises important questions about the processes that lead to the capture of moons. Did Himalia originally belong to the asteroid belt, or did it form elsewhere, perhaps beyond the orbit of Neptune, before being drawn into Jupiter's grasp? Himalia's capture by Jupiter also raises another fascinating question about the planet's role in shaping the solar system. Jupiter's massive gravitational influence could have played a pivotal role in the migration and capture of objects from the outer reaches of the solar system. Such captures could have had a profound impact on the development of planetary rings and the inner moons, stirring the dynamics of the entire solar system. If Himalia was once part of a larger object that was shattered by gravitational forces, could it still contain traces of the original body's composition? Does it harbor secrets about the primordial material that formed the outer solar system, or perhaps insights into the materials present in the Kuiper belt and beyond? Additionally, studying these moons could reveal more about the conditions necessary for life. The farthest moons in our solar system, many of which are icy and frigid, may not seem like they could harbor life at first glance. However, much like Europa or Enceladus, the deep interiors of some of these moons could contain subsurface oceans kept warm by tidal heating. These environments could potentially be capable of supporting microbial life, much as scientists speculate may be possible on Europa. Investigating the internal dynamics of moons like Hyperion, Nereid, and Himalia could offer us more insight into the likelihood of life in places we once considered inhospitable. It's also worth noting that many of these moons are likely remnants of larger objects that once existed in the solar system. For example, Hyperion and Himalia, both of which have irregular shapes and unusual orbits, might be fragments of larger bodies that were torn apart by gravitational forces or catastrophic impacts. The ongoing study of their orbits and compositions could provide crucial clues about the violent history of the solar system, including the processes that led to the formation of the gas giants and their moons. While it's clear that we have much to learn, these moons are not likely to remain forgotten for long. As space exploration progresses, we will be able to uncover more and more details about these distant worlds. The upcoming missions to Uranus and Neptune, for example, will undoubtedly shed new light on the outer solar system and its moons, potentially offering answers to many of the questions that have remained elusive for so long. One area where these moons could provide valuable information is in the study of moon-planet interactions. As we have seen with moons like Europa, Titan, and Enceladus, moons that are close to their parent planets experience tidal forces that can generate significant internal heating. This tidal heating can lead to the presence of subsurface oceans, which in turn may provide favorable conditions for life. The moons on the outer edges of the solar system, like Nereid and Himalia, might exhibit similar phenomena, providing a natural laboratory for studying how tidal forces shape the geology and potential habitability of moons. Moreover, the exploration of these moons could open the door to understanding how planetary systems develop and evolve over time. The irregular moons in our solar system are often considered to be remnants of older systems that were disrupted during the formation of their current planets. By studying their orbits, compositions, and geologies, scientists could begin to piece together the larger picture of how moons and planets form and interact. This could even have implications for our understanding of exoplanetary systems, helping us understand how other planetary systems outside our own may evolve. In the grand scheme of space exploration, the forgotten moons of the solar system are often overlooked in favor of more well-known bodies like Europa or Titan. Yet, these moons are essential to the larger story of our solar system's formation and evolution. They are time capsules, preserving information about the early solar system that could help answer some of humanity's biggest questions about the origins of planets, moons, and potentially even life itself. As we continue to probe these distant worlds, we will no doubt uncover many more surprises. With every discovery, we get one step closer to understanding the intricate dance of gravitational forces, the dynamic interactions between moons and planets, and the complex processes that shape the solar system we know today. And as we push further into space, these forgotten moons may hold the keys to future exploration, offering us a glimpse into the past while guiding us to the stars. The exploration of the forgotten moons of the solar system is more than just an exercise in uncovering secrets from the past. It is a journey into the heart of what makes planetary systems function, how they evolve, and how they can be studied from the safety of our home planet. As space exploration technology progresses, we stand on the precipice of discovering far more about moons like Himalia, Hyperion, and Nereid, and the knowledge we gain could be the foundation for our understanding of many other distant celestial bodies. One of the most fascinating aspects of these moons is their role in the broader dynamics of the solar system. For instance, the orbits of moons like Nereid, which is highly eccentric, provide valuable insights into the gravitational interactions between objects in the outer solar system. The peculiarities of these orbits may be the result of past interactions with larger bodies, such as the migration of Neptune or Jupiter, which could have destabilized the orbits of moons like Nereid, creating the erratic paths we see today. Nereid, in particular, with its odd orbit and relatively small size, stands as a reminder that the outer solar system is full of oddities and anomalies that challenge our current understanding. Its orbit may have once been circular, much like the orbits of most moons in the solar system, but the gravitational influence of Neptune could have stretched it into an eccentric shape. This kind of gravitational perturbation is a common theme in the outer solar system, where objects like Nereid and the irregular moons of Jupiter and Saturn are subject to powerful forces from the massive planets that surround them. These forces can dramatically alter the characteristics of moons over time, leading to the creation of the eccentric orbits, irregular shapes, and strange surface features that make these moons so intriguing to scientists today. In addition to Nereid, moons like Hyperion and Himalia offer fascinating clues about the formation and evolution of the outer solar system. The fact that Hyperion has such an irregular shape, neither spherical nor quite elliptical, raises questions about how such a moon could have formed. Its low density and porous structure suggests that Hyperion might be a fragment of a much larger body, possibly shattered by a massive collision. Such a violent origin story is not uncommon in the outer solar system, where moons have been repeatedly bombarded by asteroids, comets, and other debris. Hyperion's unusual appearance may be a direct consequence of these collisions, and studying it could yield valuable insights into the impact history of the solar system. Meanwhile, Himalia's retrograde orbit tells us a different story. Its capture by Jupiter's gravity could have been the result of an event in the distant past, where Jupiter's immense gravitational field swept up a wandering asteroid or comet and pulled it into orbit around the gas giant. The capture of moons like Himalia is a complex process that involves the precise balance of forces, and the unique nature of Himalia's orbit suggests that Jupiter's gravity played a key role in shaping the structure of the outer solar system. The processes that lead to the capture of moons and the transformation of their orbits are not only fascinating in their own right but also have wider implications for our understanding of planetary system dynamics. As we study the orbits and compositions of moons like Himalia, Hyperion, and Nereid, we gain a deeper appreciation for the ways in which planets and moons interact and evolve over time. These moons are like time capsules, preserving the remnants of a chaotic early solar system, and they may provide clues about how the solar system's structure took shape. The study of moons like these also feeds into the larger narrative of habitability in the solar system. While Europa, Enceladus, and Titan are often considered the primary candidates for the existence of extraterrestrial life, moons like Himalia and Hyperion may also harbor surprises. Although they are located far from the Sun and are incredibly cold, the interior dynamics of these moons could reveal hidden oceans or geothermal activity, conditions that might, under the right circumstances, support microbial life. Just as Europa's subsurface ocean has drawn the interest of astrobiologists, so too could the interiors of these moons offer a tantalizing glimpse into the potential for life in the cold reaches of the outer solar system. Beyond the search for life, the study of these moons helps us better understand the history of the solar system. Many of these moons are thought to be relics of the early solar system, remnants of larger bodies that were either destroyed by impacts or torn apart by gravitational interactions. Moons like Himalia and Hyperion could be the last traces of ancient objects that once existed in the distant reaches of the solar system. As we explore these moons, we may uncover clues about the composition of the early solar system, how material was distributed in the early solar nebula, and how the planets and moons themselves formed. The forgotten moons also offer a unique perspective on the role of gravity in shaping the structure of planetary systems. Moons that are captured by a planet's gravity, such as Himalia, provide an opportunity to study the dynamics of moon-planet interactions. These interactions can lead to fascinating phenomena, such as tidal heating, which could generate internal heat and possibly create subsurface oceans. Additionally, studying the irregular moons, those with eccentric orbits or unusual shapes, can offer insights into how gravitational forces from nearby planets can disrupt the orbits of moons, potentially leading to changes in their structure and composition over time. One important thing to consider when studying these moons is the role of gravitational resonance. Many of the irregular moons of Jupiter, Saturn, and Neptune are thought to be in gravitational resonance with other moons or planets, meaning that their orbits are synchronized in a way that creates a periodic relationship between their motions. This resonance can have a profound impact on the moon's orbital stability, and in some cases, it can even influence the moon's internal structure. For example, tidal forces generated by resonant interactions can lead to the generation of internal heat, which may play a key role in the evolution of the moon's surface and potential habitability. The more we learn about moons like Himalia, Hyperion, and Nereid, the more we realize just how much they can tell us about the history of our solar system. These forgotten moons are not just relics of a bygone era. They are active participants in the ongoing evolution of the solar system. By studying their orbits, compositions, and geological features, we can begin to piece together the story of how the solar system formed, how it evolved, and how it might continue to change in the future. And as our exploration of these distant moons continues, we may uncover new insights that could shape our understanding of the cosmos in profound and unexpected ways. In the coming decades, as space missions continue to push the boundaries of exploration, we will no doubt see more attention paid to these forgotten moons. They may not have the same level of public recognition as Europa or Titan, but their mysteries are no less fascinating. From the irregular shapes of Hyperion to the eccentric orbits of Nereid, these moons are full of stories waiting to be told. As our knowledge of the outer solar system deepens, we will undoubtedly uncover even more mysteries that challenge our understanding of the universe and our place within it. The forgotten moons are waiting to be discovered, and the journey to uncover their secrets promises to be as awe-inspiring as the cosmos itself. As we continue to explore these lesser-known moons, we must also consider the profound implications that their study has for future space exploration. The discovery of new moons, or the detailed study of those already known, can pave the way for future missions that might unlock further mysteries of the outer solar system. Whether it's through more advanced telescopic observations or sending probes to these moons themselves, the potential for groundbreaking discoveries is immense. Currently, our closest insights into these forgotten moons come from telescopic observations, such as those from the Hubble Space Telescope, and data gathered by past missions like NASA's Voyager probes and the more recent Juno spacecraft. These observations have provided us with crucial information about their size, shape, and orbits, but there is still so much more to uncover. For example, we have yet to truly understand the geological features of moons like Himalia and Hyperion. Do they harbor surface features that tell stories of ancient impacts or volcanic activity? Do they hold hidden reservoirs of water or signs of past heating? These are the questions that can only be answered by dedicated space missions. One such mission, which could provide unprecedented insight into these moons, would be a probe sent to explore Jupiter's irregular moons, including Himalia. A dedicated mission could study their surface features, composition, and magnetic properties in detail, and it could be instrumental in understanding how these moons formed. For example, could Himalia be a captured asteroid, or was it once a larger body that was torn apart in a collision? A detailed study of its surface and interior could answer these questions. Such a mission could also assess the possibility of past or present geological activity, searching for signs of subsurface oceans or volcanic eruptions, features that could point to potential for habitability. As technology advances, we may even have the ability to land on some of these moons, or at least send robotic landers to study them directly. This could provide more direct evidence of their composition and allow scientists to conduct experiments on the spot, something that telescopes and flybys can't provide. Landing on Himalia or Hyperion might seem far-fetched today, but just as missions to Mars and the Moon were once considered impossible, exploring the outer moons of the solar system could one day become a reality. Space agencies are already considering missions to the moons of Saturn, such as Titan and Enceladus, which have more widespread recognition. However, if these missions are successful, they could open the door for future missions to even more obscure moons. Another exciting prospect for exploration comes from the possibility of discovering the remnants of ancient processes on these moons. Some of the outer moons of Jupiter, Saturn, and Neptune could hold clues to the early solar system's violent past. For instance, moons like Hyperion and Himalia could have experienced a history of significant collisions, which could have fragmented larger bodies into the moons we see today. Understanding the material compositions of these moons could give us a clearer picture of the types of objects that once populated the outer solar system. Hyperion's unique irregular shape is particularly intriguing in this regard. It could have been a larger, spherical body before it was subjected to a massive impact. The fact that its surface appears sponge-like and porous suggests that it may have been weakened or shattered by past collisions. Such an event could have left behind an uneven surface and fragmented pieces scattered across the moon. Studying Hyperion's surface in greater detail may help to understand the mechanics of such impacts and how they could alter the dynamics of the outer solar system. Similarly, Himalia's composition and retrograde orbit suggest it could have originated from outside the Jupiter system, potentially from the Kuiper belt or even the Oort cloud. If this is the case, studying Himalia's surface could reveal key information about the building blocks of the outer solar system and the processes that led to the formation of the gas giants. The retrograde orbit of Himalia, in particular, is an anomaly in the context of the solar system's standard orbital mechanics, and understanding why it orbits in this manner could yield insights into how planetary systems evolve and how gravitational interactions can shape the trajectories of celestial bodies. While it's easy to focus on the better-known moons of Jupiter and Saturn, the forgotten moons, those that orbit in the distant reaches of the solar system, are just as important in helping to complete the cosmic puzzle. They give us a glimpse into the vast complexity of the solar system, showing us that there are still many unanswered questions about the formation and evolution of planetary bodies. Moons like Nereid, Hyperion, and Himalia remind us that there is still so much more to discover about our solar system, and the answers may lie in these distant and mysterious places. Looking beyond the solar system, studying these moons also gives us context for understanding exoplanets and their moons. Many of the processes that govern the formation and evolution of moons around our own planets could be applied to other star systems. By studying moons like Nereid and Hyperion, we can better understand the dynamics of exomoons, moons that orbit planets around stars other than the Sun. Such knowledge is crucial as we continue to search for potentially habitable exoplanets, and as we develop the technology to explore these distant worlds. In the grand scheme of the universe, our own solar system is just one among billions, but the lessons we learn from studying its forgotten moons could provide universal insights into the workings of all planetary systems. If there's one thing that space exploration has consistently shown us, it's that the universe is full of unexpected wonders, and the secrets of the solar system's forgotten moons could hold the key to unlocking the mysteries of not only our own cosmic neighborhood but also the universe at large. As we look to the future of space exploration, it is clear that these forgotten moons will play a central role in our understanding of the cosmos. They serve as reminders that there is always more to discover, even in the familiar regions of space that we thought we knew well. The study of Himalia, Hyperion, Nereid, and other similar moons will help to deepen our understanding of the origins of the solar system and provide new perspectives on the forces that shape planetary bodies. The forgotten moons of the solar system are not merely remnants of a distant past. They are active participants in the ongoing story of the universe. They represent the untold stories of the outer solar system, and with every new discovery, we move closer to understanding the complex forces that govern the cosmos. Their mysteries are far from forgotten. They are waiting to be uncovered, and the answers they hold could reshape our understanding of the universe in ways we are only beginning to imagine. As the exploration of these enigmatic moons continues to develop, the scientific community is buzzing with potential future missions and the vast knowledge we could gain. The outer reaches of our solar system are rich with untapped data, and moons like Himalia, Hyperion, and Nereid hold the potential to reveal more about the formation of planets and the history of our solar system than we could ever anticipate. While much of the focus has remained on moons like Europa and Titan due to their potential for harboring life, these forgotten moons might hold the keys to a broader understanding of the early solar system and the complex processes that shape the bodies within it. One of the most intriguing aspects of these moons is their potential for harboring evidence of ancient events. Most of these moons are believed to have been part of a violent and chaotic process in which many objects collided and broke apart, reshaping the landscape of the outer solar system. The shattered remains of larger bodies may have formed these moons, and the debris and fragments they contain could tell us about the types of collisions that took place during the solar system's infancy. Understanding these catastrophic events could provide insights into the processes that not only shaped our solar system but also influenced the development of other star systems. Himalia, for example, is one of Jupiter's larger irregular moons, and its retrograde orbit suggests it didn't form in place but was captured by the planet's strong gravitational field. This capture event could have involved the collision of a body from the Kuiper belt or beyond, a process that might have been repeated numerous times throughout the solar system's history. By examining the characteristics of Himalia and its orbit, scientists could better understand the mechanics of planetary captures and the likelihood that other star systems might also have similar processes at work. Hyperion, with its bizarre, irregular shape and spongy surface, is equally mysterious. Its chaotic rotation is another feature that piques scientists' interest. Unlike most moons, Hyperion rotates in a non-periodic fashion, meaning it doesn't spin at a steady rate. This behavior is likely due to its highly irregular shape and porous structure, which could have been influenced by past impacts. Understanding why Hyperion behaves this way could shed light on how objects in the outer solar system were affected by the gravitational forces of nearby gas giants like Saturn. Furthermore, Hyperion's surface is dotted with craters, some of which may have originated from impacts billions of years ago, providing a history of the violent environment in which it resides. Nereid, Neptune's most unusual moon, provides a different set of questions. Its highly elliptical orbit, which takes it from very close to Neptune to far beyond the orbit of Triton, is unlike anything seen in other moons of the outer solar system. This irregular orbit suggests a violent past, potentially influenced by the gravitational tug of Neptune's other moons or by external forces from the early solar system. Some scientists speculate that Nereid could have been a captured body, much like Himalia, and its eccentric orbit might be a result of interactions with Neptune's massive gravity. Understanding Nereid's origin could provide valuable insights into the dynamics of captured moons and the processes that influence the orbits of bodies in the outer reaches of the solar system. The more we learn about these moons, the clearer it becomes that our understanding of the solar system's formation is incomplete. While much of the focus has been placed on the inner planets and the more prominent moons like Europa and Titan, it's in the outer solar system, on the fringes of our planetary system, where the most revealing discoveries might lie. These moons, though forgotten by many, hold a treasure trove of information about the violent processes that shaped our solar system, and they could provide crucial data for understanding the formation of other planetary systems as well. The mystery of how these moons formed, what they are made of, and what secrets their surfaces hide continues to captivate scientists. If we are to truly understand the history of our solar system, we must pay closer attention to these forgotten moons. They are more than just relics of a distant past. They are key to unlocking the origins of planetary systems. Whether it's Himalia's retrograde orbit, Hyperion's chaotic rotation, or Nereid's eccentric trajectory, each of these moons offers a unique perspective on the processes that shape the planets we know today. As we continue to improve our technology and methods for exploring the farthest reaches of our solar system, the potential for new discoveries becomes ever more exciting. Advanced telescopes, like the James Webb Space Telescope, could soon offer more detailed views of these moons, revealing surface features and chemical compositions that were previously impossible to detect. Future space missions, perhaps led by NASA or other space agencies, could send robotic spacecraft to study these moons up close, unlocking the potential to answer some of the most pressing questions about their formation and history. In addition to their scientific value, these moons might even hold surprises for the search for life beyond Earth. While the more famous moons like Europa and Titan are considered some of the most promising places to search for extraterrestrial life, these forgotten moons should not be overlooked. The conditions on moons like Hyperion or Himalia might be harsh, but they could still harbor signs of past or even present geological activity. Who knows what mysteries lie beneath their icy surfaces, waiting to be uncovered? Looking even further into the future, it is possible that these moons could play a role in future human exploration of the solar system. As space agencies develop the technology for long-duration missions to the outer planets, moons like Hyperion, Himalia, and Nereid might serve as crucial waypoints for spacecraft traveling to more distant regions of the solar system. Their unique characteristics and relative proximity to the gas giants make them excellent candidates for future robotic exploration and, possibly, even human settlement in the distant future. Even if these moons never become the focus of major missions, their study continues to shed light on the processes that govern planetary formation and evolution. By studying the forgotten moons of the solar system, we are not only gaining a better understanding of our own cosmic neighborhood, but we are also paving the way for future exploration of other star systems. The lessons we learn from these moons can help us interpret the dynamics of exoplanetary systems and provide new insights into the fundamental processes that shape the universe. The forgotten moons of the solar system may be distant and obscure, but they are far from insignificant. Their study offers valuable insights into the violent history of our solar system, the dynamics of planetary bodies, and the formation of moons and planets. In many ways, they are the hidden gems of the solar system, and as technology advances, we may discover that these moons hold secrets that could revolutionize our understanding of the cosmos. In the years to come, as we continue to explore the outer reaches of the solar system, it will be these forgotten moons that could hold the answers to some of the most profound questions about the origins of our solar system and the universe as a whole. The secrets they hide are waiting to be uncovered, and the discoveries made will no doubt inspire future generations of scientists and explorers to look beyond the known and venture into the mysteries that still remain hidden in the far reaches of space. As we continue to delve deeper into the mysteries surrounding the forgotten moons, the importance of understanding their roles in the broader context of the solar system becomes even clearer. These moons are not merely passive objects orbiting distant planets. They are active witnesses to the grand processes that have shaped the very architecture of the solar system. By exploring these lesser-known moons, we are peeling back the layers of cosmic history, revealing the interactions, chaos, and forces that have made our solar system the way it is today. Looking at the orbital dynamics of these moons, we gain insight into the complex gravitational interactions that occur within the solar system. For example, Nereid's highly elliptical orbit hints at a tumultuous past filled with gravitational perturbations, possibly due to interactions with Neptune's other moons or the presence of larger objects in the Kuiper belt. These orbital eccentricities serve as natural time capsules, preserving the memory of ancient celestial events that might have otherwise gone unnoticed. If we can decode these orbital patterns, we may be able to infer how the outer solar system was shaped by external forces and the gravitational ballet between planets, moons, and other objects. Hyperion, with its peculiar chaotic rotation, offers a unique opportunity to study how irregular objects in the solar system behave under the influence of nearby planetary bodies. Unlike other moons that maintain a regular, predictable rotation, Hyperion's rotation is constantly changing in an erratic manner. This behavior may be due to its highly irregular shape and its interactions with Saturn's gravity. The fact that Hyperion has such a strange rotational pattern could be indicative of the way many irregular moons behave and how they evolved over time. The study of Hyperion's chaotic rotation could shed light on the fundamental physics governing the motions of small celestial bodies in gravitationally dynamic environments. The surface features of moons like Himalia also offer a fascinating glimpse into the history of our solar system. Himalia's relatively pristine surface, marked by large craters and relatively few signs of erosion, suggests that it is an ancient body. It has remained largely unchanged since its formation, preserving the impacts of cosmic events that occurred billions of years ago. Studying these craters could provide a clearer picture of the bombardment phase that shaped the early solar system. The large impact basins on Himalia may have been formed during the late heavy bombardment, a period when the inner solar system was bombarded with asteroids and comets. Understanding how these impacts shaped Himalia's surface could offer valuable information about the distribution of objects in the early solar system and how they interacted with the planets. It is also worth noting that while these moons may not have the same allure as Europa or Titan in terms of their potential for harboring life, they still offer a wealth of information about the fundamental processes that make up planetary bodies. Each of these moons, whether it's the icy surface of Nereid, the chaotic spin of Hyperion, or the ancient surface of Himalia, has its own unique characteristics that tell us something about the processes that drive moon formation and evolution. The more we learn about these moons, the more we realize that they could provide the missing pieces of the puzzle when it comes to understanding the solar system's past. In the search for answers about the origin of the solar system, studying these moons is essential. While much of the scientific community has focused on moons like Europa, with its potential subsurface ocean, or Titan, with its thick atmosphere and organic chemistry, the moons of the outer solar system, Himalia, Hyperion, and Nereid, are equally important in understanding how our solar system came to be. These moons may not be as conducive to life, but they offer a different set of data that can tell us about the early solar system's violent history, the nature of celestial impacts, and the complex forces that shape planetary bodies. The future of exploring these moons is incredibly exciting, especially as technology advances. The possibility of sending robotic probes to these distant moons has never been more feasible. While current space missions are focused on more well-known targets like Europa and Titan, there is a growing interest in exploring the outer reaches of the solar system. Missions like NASA's James Webb Space Telescope and ESA's JUICE mission are set to offer new insights into the moons of Jupiter and Saturn, and future missions may well venture out to study the forgotten moons in more detail. Even beyond robotic exploration, there is a growing interest in human exploration of the outer solar system. While human missions to the distant gas giants may still be far off, the moons of the outer solar system could become crucial targets for future missions. The unique characteristics of moons like Hyperion or Himalia make them potential candidates for landing sites in the distant future. If humanity is to extend its reach into the outer solar system, these moons could serve as stepping stones for exploration, offering valuable resources and scientific data that will help future missions continue to unravel the mysteries of space. In the quest for understanding the origins of life and the nature of our universe, the study of these forgotten moons may reveal unexpected connections and provide us with new ways of thinking about the formation of planetary systems. As our understanding of the solar system expands, these moons could serve as critical pieces in the puzzle, showing us how the violent processes of the past have shaped the planets and moons we know today. We may also find that these moons hold surprising connections to other celestial bodies in the solar system. For instance, the moons of Neptune, including Nereid, could provide clues about the history of Triton, which is believed to have been captured by Neptune's gravity. If Nereid is indeed a captured object, its history could be linked to the capture of other moons in the outer solar system, revealing a broader story of gravitational interactions and cosmic collisions. Similarly, the study of Himalia's surface could offer insight into the formation of Jupiter's other moons, such as Callisto and Ganymede, and help us understand the broader history of the gas giant's moon system. As we continue to explore the forgotten moons of the solar system, we are reminded of how much we still have to learn. These moons, though often overlooked in favor of their more famous counterparts, are an invaluable source of knowledge about the solar system's past. Their unique characteristics, mysterious behaviors, and ancient surfaces provide us with a window into the processes that have shaped our cosmic neighborhood. In the coming decades, as we develop new technologies and expand our reach into the outer solar system, we will undoubtedly learn more about these forgotten moons and the mysteries they hold. Whether it's through new telescopic observations, future spacecraft missions, or robotic landers, the secrets of Himalia, Hyperion, Nereid, and their counterparts will continue to captivate scientists and inspire new generations of explorers. By paying attention to these forgotten moons, we not only enhance our understanding of our own solar system but also set the stage for future exploration of other star systems. The lessons we learn from these moons will likely have implications far beyond our solar system, helping us understand the formation of moons, planets, and even life across the universe. The forgotten moons of the solar system are more than just distant, icy bodies in the void of space. They are the silent witnesses to the birth of our solar system, holding clues that could answer some of the most profound questions in science. As we continue to explore and study these moons, we will undoubtedly uncover even more mysteries and deepen our understanding of the cosmos. As we venture further into the study of these forgotten moons, it's clear that they hold much more than just historical significance. The forgotten moons, Himalia, Hyperion, Nereid, and others, represent a critical opportunity to unravel mysteries of solar system formation, gravitational interactions, and planetary science that could echo through the future of space exploration. One of the key areas in which these moons offer intriguing possibilities is their composition. While moons like Europa and Titan are rich with organic material and water, giving them potential as candidates for extraterrestrial life, the moons in the outer solar system, such as Himalia and Hyperion, may not share those same traits. However, their composition still carries enormous scientific value. The differences in these moons' surface features and chemical compositions offer a contrasting perspective on how moons develop in different parts of the solar system. Himalia, for instance, is thought to be a captured asteroid from the Kuiper belt. This hypothesis suggests that Himalia could be a remnant of a larger, primordial object that never coalesced into a full-fledged planet. Its composition, predominantly rock with some ice, fits this idea well. The study of Himalia's surface and internal composition could provide insights into the material that existed in the outer solar system during the formation of Jupiter's moons. Additionally, its status as a captured object suggests that the outer solar system's gravity wells played a major role in the reshaping of smaller bodies into moons and asteroids. By understanding how Himalia was captured, we could learn more about the processes that govern the movement and formation of objects in the solar system, potentially applying that knowledge to exoplanetary systems. Hyperion, on the other hand, stands out not just for its chaotic rotation but also for its composition and texture. Hyperion is mostly composed of a very porous, spongy material, which makes it one of the least dense moons in the solar system. Its low density suggests that it could be made of a mixture of water ice and other volatile compounds. Hyperion's surface is covered in dark material, which contrasts sharply with the icy surfaces of Saturn's other moons. The dark material could be the result of chemical reactions involving the moon's surface, interacting with Saturn's magnetosphere. Hyperion's bizarre surface features, including its craters and irregular texture, indicate it has been subjected to numerous impacts, which in turn could have altered its surface chemistry. Understanding the nature of these impacts and how they have affected Hyperion's surface could reveal how moons are altered by constant bombardment over eons. As we study the composition of these moons, we also begin to better understand the relationship between moons and their parent planets. For example, the relationship between Nereid and Neptune is particularly fascinating due to its highly elliptical orbit. It suggests that Nereid might have been affected by Neptune's gravity in such a way that it was pushed into a highly eccentric orbit. The eccentricity of its orbit is so high that it might even be a clue to the early dynamics of Neptune's moons and how they were influenced by nearby planets and the Kuiper belt. Moreover, Nereid's orbit could reveal the presence of undiscovered bodies that might be affecting its trajectory, offering insights into the gravitational interactions at the farthest reaches of the solar system. When we shift our focus to the broader implications of studying these moons, their significance becomes even more evident. These moons are not just relics of a bygone era. They are active participants in a cosmic system that continues to evolve. The history of moons like Himalia and Hyperion is a testament to the chaotic early solar system, where gravity, impact, and cosmic events shaped the celestial bodies we see today. These moons might not be as flashy as Titan or Europa, but they serve as valuable pieces in the puzzle of understanding the history and evolution of the solar system. As we push our exploration of these forgotten moons further, we also gain the chance to refine our understanding of the entire solar system. The knowledge gained from studying Himalia, Hyperion, and Nereid could be extrapolated to moons in other systems, potentially informing the study of exoplanets and their satellites. The processes that shaped the moons of Jupiter, Saturn, and Neptune could also have occurred in distant star systems, and understanding these processes could unlock secrets of planet formation on a universal scale. Another critical aspect of these moons is their potential role in the solar system's history of water. While the icy moons of Saturn and Jupiter are known to harbor subsurface oceans, there's a possibility that moons like Himalia and Hyperion could also have held liquid water in their distant past. The study of these moon surfaces and their potential for subsurface water could open up new avenues for astrobiology, helping us understand how water behaves in the outer solar system and whether life could have existed or could exist on these moons. Though the chances of life being found on these moons are slim compared to Europa or Titan, the knowledge we gain from studying them could influence how we search for life elsewhere in the universe. The scientific and exploratory value of these moons is not limited to their physical characteristics alone. The lessons we learn from Himalia, Hyperion, Nereid, and others will shape the future of space exploration. These moons are the stepping stones for developing technologies and methodologies needed to explore the outer solar system. As we continue to improve our spacecraft, increase our observational capabilities, and refine our understanding of space science, missions to these moons may become a priority for future space missions. In particular, new generations of telescopes, like the James Webb Space Telescope and ground-based observatories, will be critical in expanding our knowledge of these forgotten moons. With improved resolution and sensitivity, these instruments can provide more detailed images and spectral data, allowing scientists to better understand the compositions, atmospheres, if any, and surface features of these moons. The data gleaned from these telescopes will likely inform future flybys and lander missions, such as those we see with Europa Clipper and Dragonfly, which will explore Titan, potentially extending our reach to moons that are currently out of reach. In addition, more specialized robotic probes could be developed to specifically target moons like Himalia and Hyperion. These missions could focus on studying their surface and subsurface properties, analyzing the materials that make up these moons, and examining their potential for water or other volatiles. One exciting possibility is the development of small, modular landers or rovers that could be sent to these moons, allowing us to conduct hands-on investigations of their surfaces. These missions, although they may seem far off, are a natural extension of our growing desire to explore the less charted regions of the solar system. What's fascinating is that as we continue to uncover more about these moons, we may find new kinds of moons altogether. The discovery of an entirely new type of moon, one that doesn't fit neatly into the categories we have now, could fundamentally change our understanding of the solar system's formation and evolution. These moons could offer evidence of rare celestial processes that have not been observed anywhere else, providing invaluable information about the broader forces at play in the cosmos. These forgotten moons are also a reminder of how much there is left to discover about our own solar system. Despite all the missions to planets and moons, there's still so much about the farthest reaches of the solar system that remain shrouded in mystery. The moons of the outer planets, especially those that are more distant and less studied, offer a treasure trove of information waiting to be uncovered. As we continue to study these moons, we gain new insights into not only the solar system but also the nature of moons in other star systems and the processes that govern them. As we prepare for the future, the moons of the outer solar system should not be forgotten. Just because they're not the largest or most famous moons doesn't mean they're not important. In fact, the more we study them, the more we realize just how crucial they are to understanding the solar system's history and its ongoing evolution. These moons may be forgotten in the sense that they are not as well known as their more famous counterparts, but their role in the grand scheme of things is undeniable. They are part of the solar system's family, and each one holds its own set of mysteries waiting to be unlocked. The mysteries surrounding these forgotten moons may seem trivial compared to the more prominent bodies in the solar system, but the importance of understanding them cannot be overstated. They are not just remnants of ancient history, they are crucial pieces in the puzzle that continues to shape our understanding of space, gravity, and celestial formation. As we explore these moons, we're given more than just snapshots of frozen ice or jagged rock. We are offered a window into the fundamental processes that govern the birth and evolution of the solar system. For example, Nereid's irregular orbit around Neptune isn't just a quirk of gravity, it's an important indicator of the dynamic nature of the outer solar system. Its eccentric path suggests a gravitational history rich with interactions between Neptune, its moons, and the distant objects in the Kuiper belt. This irregular orbit is likely the result of some early catastrophic event, possibly a collision or an encounter with another large body that altered Nereid's trajectory forever. This provides insight not just into the history of Neptune's moons but into the broader dynamics of the outer solar system. These moons serve as ancient witnesses to the gravitational interactions that continue to shape the fates of other moons and objects in this distant region. The moons of the outer planets also offer insight into the complex relationship between moons and their parent planets. Titan, Europa, and Ganymede may get much of the attention due to their potential for hosting life or their fascinating surface features, but smaller moons like Hyperion and Himalia reveal just as much about the forces of nature. They show us that a planet's gravitational pull is not a one-way street. Just as a planet shapes its moons, moons can also affect the characteristics of their planets through tidal interactions and orbital resonances. These interactions can influence everything from a moon's surface activity to its orbit, and they may even lead to surprising revelations about the planets themselves. The forgotten moons of the outer solar system, Himalia, Hyperion, Nereid, and others, may not have the grandeur or intrigue of Titan or Europa, but in many ways, they are just as important for the broader understanding of celestial bodies. Each moon tells a unique story, contributing to the wider narrative of the solar system's evolution. From their capture into orbit to their subsequent transformations through impacts, tidal forces, and gravitational interactions, these moons offer a rare glimpse into the complex, dynamic processes that shape not only the solar system but potentially other planetary systems as well. Another fascinating aspect of these moons is how they challenge traditional thinking about moon formation. The assumption that moons form from the accretion of debris around a planet doesn't fully explain the origins of moons like Himalia, which is thought to be a captured object. The process by which Himalia became a moon of Jupiter highlights the chaotic nature of the early solar system, where objects from the Kuiper belt or other distant regions could be perturbed by gravitational interactions and sent on a collision course with the outer planets. This notion appends the idea that moons form exclusively from a planet's debris disk, suggesting instead that moons can be captured from the vast reaches of the solar system. This could have profound implications for our understanding of how moons form around other planets, especially in exoplanetary systems. Himalia is not the only moon with a mysterious origin story. Hyperion, too, holds many secrets. Its irregular, chaotic rotation hints at a violent history. Hyperion's rotation is not predictable, which means it doesn't follow a regular pattern like most moons. This could be due to a number of factors, such as an impact or gravitational interactions that sent Hyperion into its current state. The very fact that Hyperion's rotation is so unpredictable adds another layer to our understanding of how celestial bodies can evolve in seemingly bizarre and complex ways. Could this be a common feature of moons in the outer reaches of the solar system? The study of Hyperion could hold the key to understanding how moons in this region are affected by their parent planet's gravity and the turbulent processes of their formation. Furthermore, these moons' interactions with their parent planets extend far beyond mere orbits. The gravitational effects of these moons could be felt not only in the form of tidal locking or orbital shifts, but they could also influence planetary ring systems, magnetospheres, and even weather patterns. The study of these moons, therefore, does not just tell us about the moons themselves but could offer broader insights into planetary system dynamics. Take Hyperion, for example. Its chaotic rotation might influence Saturn's magnetosphere, affecting the way Saturn's rings interact with its moons. Similarly, Himalia's orbit around Jupiter might play a role in the broader gravitational dance that governs the movements of Jupiter's other moons. These subtle effects could, over time, help scientists understand the interconnectedness of moons and planets in greater detail. The study of moons like Himalia and Hyperion is also about looking beyond the traditional methods of exploration. In the past, missions like Voyager or Cassini provided invaluable data about the larger moons, but future missions could use advanced techniques to uncover even more about these distant worlds. For example, the use of gravity assists and flybys could give us detailed information about a moon's composition, internal structure, and even the presence of any subsurface oceans or volatile materials. With the advent of new technologies and telescopes, scientists are now better equipped than ever to explore these forgotten moons and unlock their secrets. These moons also present a unique challenge in terms of future space missions. Whereas Europa and Titan are often seen as prime targets for exploration due to their potential for hosting life or their active geologic processes, moons like Himalia and Hyperion may be less immediately exciting, yet they are no less important. To study these moons would require missions that are focused on understanding their geological and chemical properties, as well as their interactions with their parent planets. This means that exploring these moons will likely require specialized spacecraft, equipped to handle the challenging conditions of the outer solar system. But as we look to the future, one thing is clear: we are only scratching the surface of what we can learn about the moons of the outer solar system. Whether it's the forgotten moons of Jupiter and Neptune or other unexplored worlds in our solar neighborhood, there is so much left to discover. These moons, though often overlooked, hold the key to understanding the solar system's past, present, and future. They are not just relics of ancient cosmic events. They are active participants in the ongoing story of our celestial neighborhood. In the grand scheme of space exploration, The forgotten moons of the solar system represent a reminder that there is always more to discover. They are not the obvious targets of interest, but in many ways, they are just as fascinating as the better-known moons. From their chaotic orbits to their peculiar surface features, these moons offer clues about the forces that shape our solar system and the broader universe. As we continue to explore, these moons will remain critical to understanding the dynamic, interconnected nature of the solar system and our place within it. The forgotten moons also present a new frontier for astrobiology, as their diverse characteristics provide a wider range of environments that could potentially support life or microbial processes. While moons like Europa and Titan have captivated the imagination with their possible subsurface oceans and organic chemistry, the outer moons of Jupiter and Neptune, Himalia, Hyperion, and Nereid might harbor some hidden surprises beneath their icy or rocky exteriors. Though we don't have definitive evidence of life on these moons, the very possibility that their environments may once have been suitable for life adds a layer of intrigue that goes beyond the more well-known moons. The idea that life could exist or have existed on these moons isn't as far-fetched as it might seem. Europa, for instance, has a subsurface ocean beneath its ice shell, kept liquid by tidal heating and radiation from Jupiter. Titan has lakes of methane, along with an atmosphere rich in organic molecules that could, in theory, support an alternative form of life. While these moons get much of the attention in astrobiology, the less talked about moons like Himalia, Hyperion, and Nereid could hold clues to understanding life's potential across the universe. Their icy and rocky surfaces suggest that they may have experienced conditions that were favorable for life at some point in their history, perhaps when they were in the habitable zone or as a result of past geological activity. The next steps in space exploration should aim to investigate these moons more closely, looking for signs of water, organic compounds, or other chemical signatures that might indicate they once harbored life. Moreover, studying these moons could provide crucial insights into the conditions needed for the development of life. Europa and Titan are often the focus because of their potential for hosting life, but the forgotten moons present an opportunity to study alternative scenarios. If the conditions on Himalia, Hyperion, or Nereid could have supported life at some point, then it broadens our understanding of what environments are suitable for life in the universe. This also prompts the question, if life could have existed on these moons, might it still exist in some form, preserved in some extreme state we have yet to comprehend? The science surrounding these moons isn't confined to their potential for hosting life either. The study of the moon's surface features could provide us with clues about the processes that shape them. For instance, Himalia, being a captured moon, holds clues about the early dynamics of the solar system, and its surface might reveal more about the material that was present in the outer solar system during the formation of the gas giants. Similarly, Hyperion's strange, spongy appearance could yield insights into how impacts have shaped moons and planetary bodies over billions of years. By analyzing the composition of these moons, scientists could better understand the types of materials that were prevalent in the outer solar system during its formation, shedding light on the ingredients for the formation of planets and moons. Hyperion's unique surface also provides an opportunity to delve deeper into the effects of space weathering. Moons like Hyperion, with their porous surface, might have been exposed to extreme conditions, including bombardment from solar radiation and micrometeorite impacts. By studying Hyperion's surface more closely, scientists can learn how small bodies in the outer solar system interact with these environmental factors. Hyperion's surface is also remarkable because of its low albedo, which means it reflects very little sunlight. This property is indicative of the presence of complex organic compounds or other materials that could have been deposited through processes like radiation. The way Hyperion's surface has evolved over time offers a unique case study of how moons in the outer solar system react to space weathering and cosmic radiation. As for Himalia, its orbit around Jupiter places it in an interesting position for future research. Being a captured object, Himalia's composition might differ from those moons that formed alongside Jupiter. Its surface could tell the story of its origins and its journey to its current location, providing scientists with a better understanding of how moons are captured by large planetary bodies and what happens to them once they are caught. Additionally, Himalia's location outside Jupiter's regular group of Galilean moons could suggest that its formation and subsequent capture occurred after the planet's initial moon system had already stabilized, opening up the possibility that there were other moons that Jupiter interacted with in the past. Nereid, one of Neptune's moons, holds a particular intrigue due to its highly eccentric orbit. While moons like Europa and Titan have been subjects of intense study because of their relatively stable orbits and potential for supporting life, Nereid's peculiar orbit suggests a violent history. It is possible that Nereid was once part of a different system, potentially captured by Neptune after a collision or interaction with another large object in the Kuiper belt. This orbit also offers a unique opportunity to study the interactions between moons and the gravitational pull of their parent planets. The orbit of Nereid could offer a snapshot of Neptune's gravitational history and its ability to capture distant objects and transform them into moons. Nereid's erratic orbit also tells us about the complex gravitational forces at play in the outer solar system. As Neptune's gravitational influence tugged at Nereid, it might have disturbed the orbits of other objects in the Kuiper belt, leading to a broader reshaping of the region's dynamics. This is crucial information for scientists who are trying to understand how the outer solar system evolved. The study of moons like Nereid could also inform our understanding of how other planetary systems behave, especially those around distant exoplanets where moons might follow similar chaotic orbits. While moons like Himalia, Hyperion, and Nereid may not be as high profile as Europa or Titan, they still offer a wealth of scientific knowledge. Each of these moons serves as a time capsule from a different point in the solar system's history, and by studying them, we can unravel stories of capture, collision, and survival against the backdrop of cosmic forces. They challenge our understanding of what moons are capable of and reveal the untold stories of the early solar system. Looking ahead, future missions to study these moons in greater detail could shed light on many of the unanswered questions we still have about the origins and evolution of the solar system. Technologies like advanced telescopes, robotic probes, and even future manned missions might be able to provide the answers that will complete our understanding of these forgotten moons. Just as we have learned so much from studying Europa, Titan, and the Galilean moons, so too will the investigation of Himalia, Hyperion, Nereid, and other overlooked moons enrich our knowledge of the solar system's past and its potential for life and habitability. The forgotten moons of the solar system are far from insignificant. They are quiet witnesses to the solar system's tumultuous history and continue to offer rich opportunities for scientific discovery. Each one, from the chaotic rotation of Hyperion to the eccentric orbit of Nereid, holds the potential to unlock a deeper understanding of how moons and planets evolve. As we continue to reach for the stars and explore the farthest reaches of space, these moons will remain an essential part of the puzzle that tells the story of our cosmic neighborhood. Their secrets, though long hidden in the shadow of their larger counterparts, will ultimately help us understand the greater forces that shape the universe. As we continue our exploration of these fascinating and mysterious moons, we must also consider how their study will impact our understanding of other moons and planets beyond our own solar system. As we peer deeper into the cosmos, many exoplanets are being discovered with their own systems of moons, some of which could have similarities to the forgotten moons of the solar system. Just as Europa and Titan have become models for the study of exomoons and their potential for supporting life, moons like Himalia, Hyperion, and Nereid could provide key insights into the formation and evolution of moon systems around exoplanets. For example, the erratic behavior of Nereid could serve as a model for studying moons with highly eccentric orbits in other star systems. It's possible that exoplanets orbiting other stars could have moons that experience gravitational perturbations similar to those experienced by Nereid, and understanding the history and nature of these interactions could give us clues to the formation of moons in distant systems. Similarly, the strange rotation and surface features of Hyperion might be a common trait of moons orbiting large gas giants elsewhere in the universe. The more we learn about these forgotten moons, the more we can extrapolate to moons orbiting planets in other solar systems, expanding our understanding of how moons are shaped by their parent planets and how they evolve over time. In addition to informing our understanding of exoplanetary systems, These moons also offer a fascinating glimpse into the broader dynamics of our own solar system. Each of these moons, the captured Himalia, the porous Hyperion, and the eccentric Nereid, provides a snapshot of a different aspect of the solar system's formation. They hold the stories of their capture or creation, the impacts they've experienced, and the forces that have acted upon them throughout their long histories. These moons don't just reflect the history of the solar system, they also serve as crucial records for understanding the behavior of moons and planets in other systems. For example, the capture of moons like Himalia could offer vital clues about the process of moon capture in general. If we look at other captured moons in our solar system, such as Neptune's Triton, we see similar characteristics. Triton, like Himalia, has an unusual orbit and is thought to have been captured by Neptune's gravity. The study of Himalia and Triton could offer insights into the mechanisms that allow moons to be captured by a planet's gravitational pull and help us better understand the likelihood of such events in other planetary systems. Moreover, these moons offer a unique perspective on the history of our solar system's outer reaches. Himalia, Hyperion, and Nereid are far from the spotlight of most space missions, and yet they could hold the keys to answering questions about the early dynamics of our solar system. By studying these moons, we can piece together the puzzle of how our solar system's outer planets, Jupiter, Saturn, Uranus, and Neptune, interacted with one another, and how their gravitational forces shaped the bodies that orbit them today. The study of moons like Himalia and Hyperion could help us understand how the outer planets captured and interacted with smaller bodies, shaping the entire architecture of the outer solar system. Another important factor to consider in the study of these moons is their potential for hosting hidden geological activity. While moons like Europa and Enceladus are well known for their subsurface oceans and the potential for liquid water, less studied moons like Himalia and Hyperion could hold surprises of their own. It is possible that some of these moons may have experienced or continue to experience geologic processes that could make them interesting targets for future exploration. For instance, Hyperion's spongy surface could be the result of past cryovolcanism or another form of geological activity that has shaped its appearance. Himalia, being a captured moon, may have had a history of violent collisions or other events that could have triggered geological changes over time. This brings us to the possibility that, even if these moons do not have subsurface oceans or methane lakes, they could still harbor forms of life, or, at the very least, signs of life from the past. If they were ever in a position to support life, even temporarily, it is worth considering how we might search for such signs. Could they harbor microbial life trapped beneath their icy crusts? Or would they instead offer clues to the environments that may have supported life in the distant past? The mysteries that Himalia, Hyperion, and Nereid hold could expand the boundaries of what we consider to be habitable conditions in the solar system, giving us a better understanding of life's resilience. In the search for life, it's important to note that these moons, though seemingly forgotten, are not forgotten in the eyes of scientists. Mission proposals to explore these moons may not be as frequent as those to Europa or Titan, but the data we have gathered from previous observations through telescopes and flybys is enough to spark curiosity. NASA's James Webb Space Telescope, launched in 2021, has the capability to study distant moons with great precision. While the focus of the telescope has primarily been on stars and galaxies, its ability to observe distant objects in our solar system could provide new insights into the composition and history of these outer moons. In the coming years, we can expect new missions to further investigate these moons. NASA's upcoming missions to explore the outer solar system, like the Europa Clipper mission, could pave the way for future exploration of moons like Himalia and Hyperion. With the advancement of technology and space exploration, the forgotten moons of the solar system might no longer remain in the shadows. As our tools and understanding grow, so too will our ability to uncover the secrets of these strange, enigmatic moons. Perhaps one of the most exciting prospects for the study of these moons is the idea of sending probes to land on them. While this is still a long-term goal, the study of the surface of these moons could yield remarkable findings about their composition, history, and the forces that have shaped them. A lander sent to Hyperion, for example, could provide direct observations of its sponge-like surface, revealing more about its formation and the processes that have influenced its strange appearance. Similarly, Sending a probe to Himalia could help scientists understand its composition and whether it holds any secrets beneath its icy exterior. The forgotten moons of the solar system, Himalia, Hyperion, Nereid, and others, represent some of the most intriguing and mysterious objects in our cosmic neighborhood. While they may not be as famous as Europa or Titan, their unique characteristics, unusual orbits, and potential for harboring life make them essential targets for future exploration. These moons are time capsules that offer clues about the early solar system, the dynamics of planetary systems, and the potential for life beyond Earth. As we continue to explore the outer reaches of our solar system, these moons will undoubtedly play a key role in expanding our understanding of the universe and our place within it. With future missions and technological advancements, the forgotten moons of the solar system may no longer be neglected, but instead celebrated for the fascinating secrets they hold. Secrets that could change our understanding of the solar system, the potential for life, and the history of our cosmic neighborhood. As we venture further into the mysteries of these often overlooked moons, we come to realize that their value lies not just in what they might tell us about the past, but also in their potential to reveal insights about the future. The understanding of moons like Himalia, Hyperion, and Nereid might one day shape how we approach the exploration of distant worlds, guide the design of future space missions, and even influence the way we think about extraterrestrial life. Their stories are a testament to the complexity of our solar system, and as we continue to discover more about them, we are reminded of the vastness of what remains to be explored in our own cosmic backyard. One area where these moons could offer valuable information is in the study of planetary defense. As we continue to discover near-Earth objects, NEOs, the threat of asteroid impacts has become a key topic of concern. Moons like Himalia and Hyperion, which have likely been bombarded by impacts throughout their histories, can serve as natural laboratories to understand how smaller bodies in our solar system respond to such events. By studying the cratering history of these moons, scientists can develop a better understanding of how impacts have shaped our solar system, including Earth's own history. Additionally, the study of their surface features could provide insights into how impacts affect moon surfaces and how such impacts may alter the trajectory or composition of asteroids, helping us refine strategies for preventing potential catastrophic events. Furthermore, these moons might offer clues to the early conditions of the solar system's formation. The objects in the outer solar system are often considered relics from the solar system's infancy, having been relatively unchanged for billions of years. By studying moons like Himalia and Nereid, we can gain a better understanding of the material that existed in the early solar system and how it contributed to the formation of the planets and moons we observe today. Himalia, for instance, likely formed from the leftover material in the solar system's formation, and understanding its composition could reveal more about the processes that occurred in the distant past. Hyperion's strange appearance, part sponge-like, part cratered, could indicate that it has experienced a violent history of impact events, giving us insights into how these collisions shaped the small bodies that populated the early solar system. Another intriguing possibility is that these moons could hold important clues about the existence of life beyond Earth. While moons like Titan and Europa are often considered the most promising candidates for harboring life, we shouldn't overlook the potential of moons like Hyperion and Nereid. The presence of organic compounds, water, or other conditions favorable for life on these moons remains in open question. Could there be hidden oceans beneath the surface of Himalia or Hyperion? Could Nereid's eccentric orbit indicate that it once had conditions conducive to life in its distant past? While it's a long shot, the discovery of even microbial life or the conditions that could support life elsewhere in our solar system would dramatically expand the scope of our search for extraterrestrial life and fundamentally change the way we think about the uniqueness of life on Earth. Furthermore, these moons offer an opportunity to explore how celestial bodies evolve and adapt to their environments over time. For example, Hyperion's bizarre rotation could give clues about the forces at play when moons interact with their parent planets. Is its odd spin due to its low density and porous structure, or does it reflect more complex interactions between Hyperion and Saturn's powerful gravity? Similarly, the capture of moons like Himalia provides a valuable case study in how planets can steal satellites from other parts of the solar system, shedding light on the dynamic nature of planetary systems. The irregular orbits of moons like Nereid offer a glimpse into the chaotic gravitational interactions that must have occurred when the outer solar system was still young, highlighting the potential for gravitational slingshots and planetary migrations. While there has been a focus on the more famous moons like Europa, Titan, and Ganymede, the forgotten moons serve as important reminders that there is still so much we have yet to uncover. The exploration of moons like Himalia, Hyperion, and Nereid could yield surprises that challenge our understanding of planetary formation, moon dynamics, and the possibility of life elsewhere in the solar system. For this reason, they should not be overlooked in the search for answers to some of the most fundamental questions in science. In the coming decades, we may see increased attention and investment in studying these moons. The advancements in technology, such as more powerful telescopes, improved space probes, and greater computational modeling, will allow us to uncover more about these distant objects. Future missions, including orbiters, landers, and even sample return missions, could provide a wealth of new information, potentially uncovering answers to questions that have long been left in the dark. These moons may not be the primary targets of missions like those to Europa or Titan, but they are just as important for expanding our knowledge of the solar system. We are on the verge of a new era in space exploration, one where even the most distant, neglected corners of the solar system are brought into the spotlight. As our tools and understanding improve, we can expect to see a resurgence of interest in the forgotten moons, and with that interest, a wealth of new knowledge about our solar system and beyond. What once seemed like distant, enigmatic bodies will soon reveal their secrets, contributing to our ever-growing understanding of the universe. And in the process, the forgotten moons of the solar system will no longer be forgotten but celebrated for the unique and valuable contributions they make to our understanding of the cosmos. The journey to unravel the mysteries of moons like Himalia, Hyperion, and Nereid is not just about discovering what is hidden on these moons, it's about discovering what they can teach us about the solar system as a whole. As we reach farther into space, we will find that the forgotten moons have much to say about the origins of the solar system, the history of planetary evolution, and even the potential for life beyond Earth. These moons, once neglected and overlooked, are now essential to our quest for knowledge about the universe. And as our exploration continues, we may find that the most unexpected places hold the greatest discoveries. As we push forward into this era of exploration, there's one more crucial aspect to consider: the hidden treasures these moons might be hiding beneath their surfaces. While much of the attention has been focused on surface-level features like craters and icy plains, what lies beneath could be even more significant. The outer moons of the solar system, particularly those like Hyperion and Himalia, are often thought of as being cold and barren. Yet, could there be more to these moons than meets the eye? In the case of Titan, one of Saturn's most famous moons, we know there's an atmosphere and liquid methane lakes that hint at a complex system beneath the surface. Europa, with its subsurface ocean, has long been a prime target in the search for extraterrestrial life due to its potential to harbor life in the liquid water below the icy crust. This has sparked questions about whether the more neglected moons, like Himalia or Nereid, could similarly host some form of life or crucial conditions for life to exist, even if in radically different environments than Earth's. If the outer solar system's moons, less studied and observed, hold hidden underground oceans or chemical compounds, we might be one step closer to uncovering the larger, unanswered questions of life's potential beyond Earth. Imagine a scenario where, much like Titan, a probe or lander successfully discovers organic molecules or even microbial life under the surface of one of these moons. This could open a new chapter in the study of astrobiology, confirming that life isn't confined to the rocky worlds we are familiar with but could exist in a multitude of environments, from gas giants like Saturn and Jupiter to the icy moons that orbit them. If this kind of discovery were to be made on a less discussed moon, it would make waves in the scientific community. It would suggest that life could thrive under conditions we hadn't previously imagined, dramatically altering our approach to the search for life elsewhere in the universe. Furthermore, these moons could have much more to tell us about the broader dynamics of the solar system. For instance, the very existence of moons like Hyperion with its strange and chaotic orbit speaks to the gravitational interactions that have shaped the solar system. Hyperion's eccentric rotation and sponge-like surface have been interpreted as the result of complex gravitational forces from Saturn and its moons. Studying this could deepen our understanding of gravitational interactions on a local scale and the long-term evolution of moon systems. Likewise, Himalia, one of Jupiter's moons, is notable not just for its size but also for its irregular orbit. It's believed to have been captured by Jupiter's gravity, originating from the outer reaches of the solar system. This suggests a violent past in which objects were flung across the solar system, colliding, interacting, and often being absorbed by the massive gas giants. Such processes not only shape the moons of today but also provide clues about the early solar system's chaotic nature. Himalia is often overlooked because of its distant orbit and lack of a particularly dramatic appearance. However, the study of its orbital mechanics and composition could yield fascinating insights into the processes of planetary accretion and the migration of giant planets. Nereid, another moon of Neptune, provides yet another fascinating case. With its eccentric and elongated orbit, Nereid stands out in the outer solar system. Its orbit takes it from relatively close to Neptune to distances far beyond that of Pluto. The highly unusual shape of Nereid's orbit challenges conventional theories about the formation of moons and planetary systems. Some scientists speculate that its orbit could be the result of gravitational interactions with Neptune's other moons or perhaps even a distant planetesimal. What makes Nereid intriguing is its potential to shed light on the dynamics of the outer solar system. How do moons interact with distant planets over vast periods of time? Could moons like Nereid hold the key to understanding the forces that govern the outermost regions of our solar system? As missions continue to explore these far-flung moons, we might begin to piece together the larger puzzle of how moons form, evolve, and interact with their parent planets. While we are all too familiar with the grand discoveries made around moons like Europa, Titan, and Ganymede, the hidden gems of Himalia, Hyperion, and Nereid could provide the final pieces to understanding the greater story of our solar system's history and evolution. In many ways, these forgotten moons may be the key to answering questions about our own planet's formation and the broader workings of the cosmos. In the coming years, it is likely that new missions will push the boundaries of our knowledge further, giving us a glimpse into the many mysteries of these faraway worlds. Space agencies, such as NASA and the European Space Agency, ESA, are already planning ambitious missions to investigate moons that have remained largely unexplored. The development of better space telescopes and the advancement of landing technology could soon make it possible to study these moons in more detail, gathering data from the surface, analyzing their atmospheres, and even sampling their icy crusts to determine their chemical composition. One particularly exciting prospect is the possibility of sending missions to study these moons in person. A mission to one of these lesser-known moons could be just as groundbreaking as those to Titan or Europa, with the potential to reveal entirely new insights about the nature of celestial bodies in the outer solar system. It's entirely possible that a spacecraft, launched in the coming decades, could arrive at Himalia, Hyperion, or Nereid and unlock the secrets of their surface features, composition, and hidden histories. Imagine a future mission that deploys a lander on Hyperion, and after several months of study, it uncovers traces of complex organic molecules in its surface or detects the presence of water ice in its porous structure. Such a discovery could open up possibilities for understanding the building blocks of life in environments far more extreme than Earth's. Or picture a scenario where a probe studies the icy surface of Himalia, revealing that beneath its frigid exterior, there might be an ocean of liquid water capable of supporting life as we know it, or life in an entirely different form. What if Nereid's erratic orbit suggests that it was once home to a dynamic system of geology and chemistry, now frozen in time, preserving ancient processes that have long since stopped on other moons? These moons are not forgotten because they are unimportant. They have been overlooked because our focus has been drawn to the more famous, the more obvious targets in our quest for knowledge. But as we gain more tools to explore these distant worlds, we are uncovering the fact that these moons, like the forgotten chapters of a book, hold critical pieces of a larger, unfolding story. By paying attention to these once-ignored moons, we are taking a more holistic approach to understanding our solar system. The mysteries of Himalia, Hyperion, and Nereid are waiting to be uncovered, and in doing so, we will gain a deeper appreciation for the complexity and wonder of our own cosmic neighborhood. As we continue to explore these distant moons, it's clear that the solar system's outer realms remain rich with potential for discovery. Yet, the mysteries surrounding moons like Himalia, Hyperion, and Nereid aren't just about their current conditions. They also offer a glimpse into the early solar system and the forces that shaped it. The story of how these moons were formed and how they interact with their parent planets is a tale of cosmic chaos and order, with gravitational interactions, impacts, and migration playing crucial roles. Let's begin by considering the formation of these moons. The origins of moons like Himalia, Hyperion, and Nereid remain speculative, and unraveling their histories requires delving into some of the most fundamental processes that govern the creation of moons and planets. Many of the outer moons of Jupiter and Saturn are thought to have formed from material that was left over after the planets themselves formed. This material, composed of ice, rock, and gas, could have been pulled into the orbits of the planets through gravitational forces. This is especially evident with Himalia, which is believed to have been captured by Jupiter's immense gravity. Himalia, though large for an irregular moon, exhibits features suggesting a violent and tumultuous past. Its irregular orbit and composition suggest that it might have originated in the Kuiper belt or the scattered disk, far beyond the orbit of Neptune. This notion supports the idea that moons can be captured by the gravity of large planets, a phenomenon that is not unique to Jupiter but also seen with other large planets, including Neptune's capture of Triton. Himalia's capture likely involved significant collisions and gravitational interactions that altered its trajectory, shaping its current orbit. Studying Himalia can, therefore, provide a deeper understanding of how moons in the outer solar system are formed and how planetary systems evolve over time. Hyperion's origin story is just as intriguing. This moon's chaotic, irregular rotation sets it apart from many of the solar system's moons. Unlike the majority of moons, which rotate in a regular, stable manner, Hyperion tumbles through space, spinning in an unpredictable fashion. This is thought to be the result of its low density and porous structure, which means it has less internal cohesion than other moons. Hyperion's chaotic rotation may also be influenced by interactions with Titan, Saturn's largest moon, whose gravitational pull could contribute to Hyperion's instability. Such chaotic rotation could also shed light on the process of how moons interact with one another and how the dynamics of a moon system evolve over time. Hyperion's sponge-like surface, covered in deep craters and icy plains, further adds to its mystery. The craters on Hyperion are some of the largest in the solar system and appear to be a mix of icy material and rock. This suggests that Hyperion is composed of a relatively low-density material, possibly a mixture of water ice, rock, and porous material. The fact that Hyperion's surface is so porous could imply that it has undergone a significant history of collisions and impacts, which have left it with the distinctive features we see today. The study of Hyperion's surface could, therefore, yield insights into the processes of moon formation, the nature of impacts in the outer solar system, and the evolution of icy bodies in the cold expanse of space. Nereid, Neptune's distant and eccentric moon, is another intriguing object in the outer solar system. Its highly elongated orbit, which takes it from a distance of about 1.35 million kilometers from Neptune to a distance of around 9.6 million kilometers, is unlike any other moon in the solar system. This strange orbit has prompted scientists to speculate about Nereid's origin. Some believe that Nereid was once a captured object, possibly a Kuiper belt or scattered disk object, which was subsequently pulled into Neptune's orbit by the planet's gravity. Others hypothesize that Nereid's orbit was shaped by gravitational interactions with Neptune's other moons or possibly even with objects in the outer solar system. Regardless of how Nereid came to occupy its current position, its erratic orbit presents a valuable opportunity to study the gravitational forces at play in the outer reaches of the solar system. Nereid's surface is relatively unknown, but it is thought to be composed mainly of ice and rock, similar to other moons in the outer solar system. However, its highly inclined orbit could provide valuable clues about the history of the solar system's formation. Some scientists believe that the unique orbit of Nereid might be a remnant of the early solar system's chaotic phase, when gravitational interactions between the planets and smaller bodies led to the rearrangement of the solar system's architecture. By studying Nereid's orbit, scientists hope to gain insights into the processes that govern the early evolution of the solar system and the formation of its moons. In addition to their formation histories, these moons also provide valuable insights into the processes that govern the behavior of celestial bodies in the outer solar system. For example, the study of Hyperion's chaotic rotation and Himalia's irregular orbit sheds light on the dynamics of gravitational interactions between moons and their parent planets. Moons like Hyperion and Himalia, which are influenced by complex gravitational forces, provide a unique opportunity to study the mechanics of orbital motion and the role of gravity in shaping the structure of planetary systems. Similarly, Nereid's eccentric orbit offers clues about the gravitational interactions between moons and planets, as well as the influence of external forces on the evolution of moons over time. As we continue to explore these forgotten moons, we also gain a better understanding of the diversity of environments that exist in our solar system. While moons like Europa, Titan, and Enceladus have captured our attention due to their potential to harbor life, moons like Hyperion, Himalia, and Nereid may reveal entirely new aspects of the solar system. The outer moons of the solar system are often overlooked, but as we learn more about their characteristics, we realize that they hold key insights into the past, present, and future of our cosmic neighborhood. The next frontier of exploration may very well be focused on these overlooked moons. With future missions targeting these distant worlds, we could soon uncover new details about their surface composition, their atmospheres, and their potential to harbor life or complex chemistry. The lessons we learn from studying Himalia, Hyperion, and Nereid could have far-reaching implications for our understanding of the solar system and beyond. These moons are the hidden gems of our solar system, offering us a glimpse into the past and a glimpse of what may lie ahead as we continue to explore the mysteries of space. As we delve deeper into the forgotten moons of our solar system, the complexities of their orbits, compositions, and histories only become more fascinating. Each of these moons, whether it be Himalia, Hyperion, or Nereid, holds a key to understanding the broader mechanics of the solar system and the forces that have shaped it over billions of years. But their stories are far from over, and the more we explore them, the more mysteries emerge. One area that could yield significant discoveries is the study of their potential to reveal how moons, planets, and other celestial bodies interact. Consider the influence of tidal forces, for example. Tidal forces result from the gravitational pull that one body exerts on another, and they can have profound effects on both the moon and the planet it orbits. For moons like Himalia, Hyperion, and Nereid, understanding tidal forces is crucial to unraveling their evolutionary paths. Himalia's irregular orbit suggests that it has been subjected to tidal interactions with Jupiter, potentially causing it to shift in its orbit over time. These interactions might also explain why some of the outer moons of Jupiter have such eccentric orbits, and why their rotations are often chaotic. Hyperion's chaotic rotation, for example, is another fascinating result of gravitational interactions, likely amplified by the gravitational tug of Saturn and its largest moon, Titan. This process may also help explain the moon's unusual surface features. Hyperion's spongy, cratered surface could be a direct result of the tidal forces at play, which may have also contributed to the moon's low density and porous composition. Studying how Hyperion has been affected by tidal forces could also give insight into how such forces operate on other moons in the solar system and how they influence the moon's overall behavior. The concept of tidal locking is another interesting aspect of these moons. Tidal locking is the phenomenon where a moon's orbital period matches its rotation period, causing the same side of the moon to always face its parent planet. This effect is most evident in moons like our moon, which is tidally locked to Earth, but it may have played a role in the evolution of other moons as well. For example, Himalia, with its irregular orbit, might not yet be tidally locked to Jupiter. This suggests that its orbital evolution could still be ongoing, and understanding this process could provide valuable information about the long-term behavior of moons in the outer solar system. Furthermore, the eccentric orbits of moons like Nereid and Hyperion also open up a window into the gravitational interactions that occur at the outermost reaches of the solar system. Nereid, with its highly elongated orbit around Neptune, provides a unique opportunity to study the effects of gravitational forces at play in these distant regions. Its orbit suggests that it might have once been captured by Neptune's gravity, and its strange path could provide clues about the early evolution of Neptune's moon system. The eccentric orbit of Nereid might also be the result of interactions with other moons, possibly even the presence of nearby small bodies or objects from the scattered disk. The study of such interactions can help us understand the dynamics of gravitational capture and the formation of moons in regions far beyond the typical planetary systems we observe. Moreover, these moons offer a glimpse into the diversity of environments that exist in the solar system. While many moons around Jupiter and Saturn, like Europa and Titan, are well known for their potential to support life due to their subsurface oceans or thick atmospheres, moons like Himalia, Hyperion, and Nereid may tell a different, yet equally important, story. Their surface conditions, though harsh, could hold valuable clues about the processes that shape icy bodies, and their chaotic orbits may provide insights into the violent early years of the solar system. Take, for example, the possibility of ice volcanism on moons like Hyperion. The porous nature of Hyperion could suggest that it has experienced some form of cryovolcanism in the past. Cryovolcanism, or ice volcanism, occurs when a moon or planet erupts icy materials rather than molten rock. It's a phenomenon that has been observed on other moons, like Enceladus and Europa, and could also have played a role in shaping Hyperion's surface. The study of such phenomena could open new avenues for understanding the geological activity of icy moons and the role that water and ice play in shaping the evolution of these distant bodies. Himalia, on the other hand, is one of the largest moons in the irregular class, and its surface features provide clues about the history of the outer solar system. Unlike the ice-covered moons of Jupiter, Himalia's surface appears to be a mix of ice and rock, suggesting that it may have formed in a region of the solar system that was rich in both materials. It also has a relatively high albedo, meaning it reflects a significant amount of sunlight. This could indicate that Himalia's surface has undergone little alteration from processes like radiation or collisions, offering a relatively pristine glimpse into the early solar system's conditions. Nereid's surface remains one of the greatest unknowns of the outer solar system. Despite its highly elongated orbit, which brings it close to Neptune and then sends it far out into the reaches of the solar system, Nereid's surface has not been extensively studied. It is thought to be composed of a mixture of ice and rock, but without direct observations, it's difficult to say what exactly lies beneath its icy exterior. This presents an exciting opportunity for future exploration. If we were to send a spacecraft to observe Nereid up close, we might uncover hidden features or chemical compositions that could provide insight into the history of Neptune's moons and the nature of small icy bodies in the outer solar system. The exploration of these moons also challenges our understanding of how the solar system evolved and how its outer regions were shaped. The history of the solar system is written in the interactions between planets, moons, and other bodies, and by studying moons like Himalia, Hyperion, and Nereid, we are piecing together the puzzle of how the solar system formed and how its moons evolved over time. The chaotic orbits and unique features of these moons suggest that they may have undergone significant changes over their lifetimes. Some moons, like Nereid, may have been captured by their parent planets, while others, like Himalia, may have been shaped by interactions with other bodies in the outer solar system. The study of these moons could provide valuable information about the early stages of the solar system and the processes that led to the formation of planetary systems. While moons like Europa and Titan often dominate discussions about the search for life in the solar system, the forgotten moons of the outer solar system, Himalia, Hyperion, and Nereid, are far from inconsequential. These moons, though distant and often overlooked, play a crucial role in expanding our understanding of the solar system. Their irregular orbits, unique compositions, and tumultuous histories offer insights into the processes of moon formation, the dynamics of planetary systems, and the forces that have shaped the solar system as a whole. As we continue to explore these distant worlds, we may uncover even more mysteries, shedding light on the forgotten moons that lie at the edges of our cosmic neighborhood. As we continue to explore the forgotten moons of the solar system, it's important to understand how these moons contribute to the broader narrative of space exploration and cosmic evolution. With each new discovery, we come closer to unlocking the secrets hidden within these distant bodies. Their mysteries might not just be about their individual characteristics, but how they interact with one another and with their parent planets. They act as time capsules, preserving ancient histories and offering us a window into the distant past. Himalia, Hyperion, and Nereid, though often overshadowed by the more popular moons like Europa and Titan, tell us a different kind of story, one of survival, adaptation, and the lasting effects of gravitational interactions. Their orbits, compositions, and behaviors all provide clues about the forces at play in the early solar system, as well as the long-term dynamics of celestial bodies. Himalia, with its irregular orbit, is thought to be a captured object, perhaps once a part of the asteroid belt, or even a distant body from the Kuiper belt. Its irregular orbit is a direct result of gravitational interactions with Jupiter, which may have caused it to be captured and drawn into orbit around the gas giant. This is a reminder that moons don't always form around their parent planets. Some are captured in a process that is far more violent and chaotic than we initially realize. This process of capture is an ongoing mystery, and Himalia's orbit offers a unique case study in how planets can interact with other bodies and disrupt their trajectories. In addition, Himalia's composition could reveal more about the diversity of objects that populate the outer solar system. While Europa and Titan are known for their potential to harbor life, Himalia's rocky icy mix and its distance from Jupiter suggest a very different set of environmental conditions. Exploring this moon might offer clues about the formation of moons in the outer regions of the solar system, especially those that didn't originate in the traditional accretion disks around planets. Himalayan-type moons may be a key to understanding how the gas giants collected their retinue of moons. Could they have once been part of the Kuiper belt, or even distant comets, captured by Jupiter's immense gravity? Hyperion, with its strange, sponge-like appearance and chaotic rotation, adds another layer to our understanding of the dynamic processes shaping moons in the outer solar system. Hyperion's irregular rotation is likely the result of gravitational interactions between Saturn and its moons. This type of orbital chaos is not limited to Hyperion. Moons like it provide important clues about the interactions between a planet and its moon system. These irregularities, though often viewed as anomalies, are in fact manifestations of the gravitational forces that shape the entire solar system. Hyperion's peculiar rotation is thought to be influenced by Saturn's gravitational pull, as well as by the presence of Titan, which exerts its own gravitational influence. These complex interactions lead to the erratic motion we observe today, but they also suggest a highly dynamic and evolving system that is far from stable. The surface of Hyperion offers a remarkable record of its tumultuous past. Its highly cratered surface, with deep depressions and sharp ridges, tells a story of impact events, tidal forces, and slow changes over time. These features suggest that Hyperion may have undergone major disruptions during its history, perhaps as a result of gravitational interactions with Saturn's other moons or from impacts by objects from the outer solar system. Studying the surface of Hyperion could provide valuable information about the history of the outer solar system and the types of impacts that were common during its early formation. Then there's Nereid, Neptune's strange and distant moon, which is often overlooked in favor of its more famous counterparts like Triton. Nereid's highly eccentric orbit raises many questions about how it came to be. With a highly elongated path around Neptune, Nereid is thought to be a captured object, possibly once a member of the scattered disk. Its orbit suggests that it might have been drawn into Neptune's gravity well from a much greater distance, perhaps from the Kuiper belt or even farther out. The peculiar orbit of Nereid is a key clue to understanding how moons are captured and the role that gravitational interactions play in shaping the orbits of distant bodies. The study of Nereid could offer valuable insight into the dynamics of the outer solar system and the processes that govern the behavior of bodies in these far-flung regions. The moon's strange orbit and possible capture scenario highlight the complexity of the solar system's formation. In the case of Nereid, we are dealing with a body that may have been flung out into the farthest reaches of the solar system, only to be caught by Neptune's gravitational pull. This process of capture is one of the mysteries of the solar system, and Nereid's unusual path offers an exciting avenue for future exploration. One fascinating aspect of moons like Himalia, Hyperion, and Nereid is the potential for future missions to these distant worlds. While moons like Europa and Titan are receiving the bulk of attention due to their potential to support life, the forgotten moons of the outer solar system present an untapped wealth of scientific opportunities. These moons may not have the same allure when it comes to life, but they hold a unique place in our understanding of the solar system. Their chaotic orbits, bizarre surface features, and strange histories make them prime candidates for further exploration. A mission to one of these moons could offer unprecedented insight into the processes that govern the outer solar system, and may even reveal surprises we can't yet anticipate. The exploration of Himalia, Hyperion, and Nereid could also serve as a way to understand the larger forces at play in the formation of planetary systems. By studying how moons are captured, how their orbits evolve, and how their surfaces change over time, we can learn more about the conditions that existed in the early solar system. These moons, with their strange orbits and unique characteristics, act as living fossils that carry the imprint of the solar system's turbulent past. They offer a glimpse into the dynamic processes that shape the planets and their moons, and by studying them, we can learn more about the broader mechanisms of planetary formation and evolution. The forgotten moons of the solar system, the Himalias, Hyperions, and Nereids, are much more than just distant, frozen bodies. They are key players in the story of our solar system, and they provide valuable clues about its formation, its early history, and the processes that continue to shape it today. As we continue to explore these forgotten moons, we may uncover new mysteries and gain insights into the fundamental forces that govern the cosmos. And while these moons may have once been overlooked in favor of more glamorous targets, their stories are just beginning to be told. As we continue to delve into the forgotten moons of the solar system, the mysteries of bodies like Himalia, Hyperion, and Nereid become more profound. These moons might not be the subject of extensive missions or widespread scientific interest, but their peculiarities contribute to our growing understanding of the solar system's complex dynamics and history. For instance, the bizarre orbits of these moons not only tell us about their individual histories but also reveal the immense forces that shape the paths of celestial objects, including moons, planets, and even comets. This is an area where many of the more well-known moons fall short, and these lesser-known moons step in to fill in the gaps. Consider Himalia's capture scenario. Its orbit around Jupiter is highly irregular, which is unlike the stable, circular orbits we typically associate with moons. Himalia's orbit is much more elliptical, and its eccentric path could be a remnant of a violent capture event in the distant past. This is a scenario we don't see with the major moons of gas giants, making Himalia a unique case in the study of orbital mechanics. If Himalia did indeed originate in the Kuiper belt or beyond, it offers an interesting example of how objects from the outer solar system can be pulled into the gravitational well of a massive planet, forever altering their trajectory and behavior. This could also offer a glimpse into the past interactions of Jupiter with other bodies, potentially hinting at the planet's early history. Hyperion, with its sponge-like surface and irregular rotation, is another moon that offers intriguing clues about the forces at work in the solar system. Its erratic movement is unlike the steady rotation of most moons, but that could be a direct result of the gravitational interactions between Hyperion and Saturn's other moons. The moon's unique rotation is often seen as chaotic, yet this phenomenon speaks volumes about the dynamic processes of celestial bodies interacting over long periods. Saturn's gravity, combined with the interactions of Hyperion with other moons like Titan, creates a gravitational dance that has led to the strange rotational behavior observed today. When we look at the surface of Hyperion, we can also see evidence of tidal heating, an essential factor in understanding how moons evolve over time. Tidal forces, especially in systems with close orbits around massive planets, generate friction within the moon's interior. This process leads to heating, which can affect the moon's surface and interior composition. Hyperion's surface features, including its unusual depressions, are likely the result of such forces. Additionally, the influence of Saturn's gravity on Hyperion's orbit has probably played a role in shaping its surface over time, leading to its cratered and irregular appearance. Nereid, Neptune's distant and mysterious moon, further adds to the diversity of the solar system's moon population. Its highly eccentric orbit is a puzzle in itself. The elongation of Nereid's orbit, in particular, makes it stand out among the other moons of Neptune. Most moons tend to follow relatively circular orbits, but Nereid's orbit, which is highly elongated, is a testament to the complex gravitational dynamics at play. It could have been captured in this orbit during a very specific moment in the history of Neptune's formation, or perhaps it was gravitationally perturbed by another object in the Kuiper belt or further out. This eccentric orbit raises significant questions about how moons are captured by their planets, particularly those that exist in the outer reaches of the solar system. If Nereid is a captured object, it offers a rare glimpse into the history of Neptune and the mechanisms that govern the dynamics of moons. The mysteries of moons like Himalia, Hyperion, and Nereid also speak to a larger theme in the solar system's formation, the potential for diversity among planetary moons. These moons are not simply orbiting their parent planets in predictable, well-understood paths. Instead, they are products of highly dynamic processes that have shaped their orbits, compositions, and surfaces. The solar system is not just a collection of well-ordered objects. It is a chaotic and ever-evolving system where gravitational interactions, impacts, and orbital resonances create a complex, interconnected web of bodies. The diversity among the moons of Jupiter, Saturn, and Neptune is vast, and this variability is key to understanding the solar system's origins. Each moon tells a unique story. The inner moons of Jupiter, like Io, Europa, and Ganymede, are shaped by the powerful gravitational interactions between Jupiter and its satellites, as well as by tidal forces that create volcanic activity and surface reshaping. Meanwhile, the outer moons like Himalia reveal a different story, one of capture, long-term orbital evolution, and perhaps even collisions with other objects in the outer solar system. Saturn's moons, with their icy exteriors and complex gravitational interactions, present another unique set of challenges. The chaos in the orbits of moons like Hyperion is not random. It is the result of subtle forces that have been acting on these bodies over billions of years. The gravitational influence of Saturn itself, as well as the presence of nearby moons, has likely caused Hyperion's peculiar behavior and may also be the reason for its bizarre surface features. The relationship between Hyperion and its neighboring moons is an example of the interconnectedness of the solar system's moon systems. Even though Hyperion might seem like an isolated body in space, it is anything but. Its orbit and surface are intimately tied to the other moons of Saturn. Then, we must consider the broader picture of how moons and planets interact in the context of the solar system. The captured moons of Jupiter, Saturn, and Neptune, like Himalia, Hyperion, and Nereid, are remnants of the solar system's turbulent past. In the early solar system, collisions, gravitational perturbations, and planetary migrations played key roles in shaping the orbits of these moons. Over time, moons that were once far from their parent planets may have been drawn into orbit, while others were ejected into deep space or collided with other objects. Some moons, like those orbiting Saturn, may have originated from objects in the Kuiper belt or beyond, only to be captured by the gravitational force of Saturn. Others, like Nereid, may have been captured much later in the solar system's evolution. Each of these moons represents a fragment of this ancient history. They are the remnants of the violent processes that shaped the early solar system, and they offer a glimpse into the way moons, planets, and even the sun's formation took place. By studying these moons, whether through telescopic observations or future missions, we can uncover more about the solar system's formative years and how it evolved into the system we see today. We may also discover that these forgotten moons hold secrets about the outer solar system that are crucial for understanding planetary formation on a larger scale. As we continue our exploration of the forgotten moons of the solar system, it becomes clear that these bodies are not merely overlooked or insignificant, Each one holds keys to understanding the solar system's vast history, its chaotic formation, and the various forces at play in its ongoing evolution. The moons of Jupiter, Saturn, and Neptune, such as Himalia, Hyperion, and Nereid, are not just celestial bodies drifting aimlessly through space. They are vital components in the puzzle of the solar system's intricate and dynamic past. The forgotten moons are a reminder that, even as we gaze at the more prominent moons like Europa, Titan, and Io, the quieter, more distant moons harbor just as many mysteries and potential for discovery. While Europa and Titan captivate our attention because of their possible subsurface oceans and the potential for extraterrestrial life, moons like Himalia, Hyperion, and Nereid push us to look beyond the obvious and consider how gravitational interactions, orbital anomalies, and even past impacts might have shaped the very structure of our cosmic neighborhood. They add another layer of depth to the story of planetary and moon formation, offering us the chance to explore the edges of the solar system in ways that the major moons cannot. Looking at Himalia again, we see that its orbit is not the only oddity it possesses. Its surface, composed mostly of ice and rock, is quite similar to other outer solar system bodies, but the moon's lack of uniformity in color and surface features sets it apart from other moons of Jupiter. The chaotic nature of Himalia's orbit, highly inclined and highly elliptical, suggests that this moon didn't form in its current location but was captured in the distant past. Its relatively small size and irregular shape are consistent with the idea that it might have been a member of the Kuiper belt or the Oort cloud before Jupiter's gravity snagged it. Such a capture scenario could imply that Himalia is a relic, an object frozen in time from the early solar system. By studying its surface, scientists may be able to unlock secrets about the conditions in the outer reaches of the solar system, places where the icy bodies of the Kuiper belt and Oort cloud remain largely unexplored. It's possible that moons like Himalia could hold preserved information about the primordial conditions that existed when the outer solar system first began to form. Perhaps future missions could investigate Himalia's surface more closely, using advanced imaging and spectrometry to understand the composition of the materials that make up this forgotten moon. Hyperion, with its strange surface features and chaotic rotation, presents a different set of challenges and mysteries. It is the largest of Saturn's irregular moons, and like Himalia, it has an eccentric orbit that doesn't follow the more predictable path of moons that are gravitationally bound to their parent planet. Hyperion's orbit is influenced by the gravitational forces exerted by Saturn's other moons, creating a complex and chaotic system where Hyperion's rotation is not fixed but varies unpredictably. This odd behavior is called chaotic rotation, and it's thought to be caused by the influence of Saturn's gravity and the tidal forces exerted on Hyperion by its neighboring moons, especially Titan and Enceladus. Hyperion's spongy surface, marked by deep craters, suggests a history of high-energy impacts. Unlike the smooth, icy surfaces of moons like Europa or Enceladus, Hyperion's surface is highly porous, which might be the result of the moon's low density and the erosion caused by the relentless bombardment of meteoroids. The craters on Hyperion are not just random but appear to be aligned, leading some scientists to propose that Hyperion might have once been part of a larger body that shattered upon impact, leaving behind fragments that went on to form this peculiar moon. The chaotic nature of Hyperion's orbit and the unusual characteristics of its surface raise important questions about how moons are shaped and evolved over time. The fact that Hyperion has managed to retain its odd rotation and surface features despite being subjected to such powerful forces suggests that Saturn's moons, and the gas giants' moons in general, are far more dynamic than we have traditionally thought. Their evolution is not a simple story of steady accretion and gravitational stability, but one of constant interplay between forces both near and far, tidal interactions, impacts, and even the gravitational influence of other moons. In contrast, Nereid's irregular orbit tells a different story. With its highly eccentric orbit around Neptune, Nereid's behavior is far less understood, though its orbit suggests it was likely captured by Neptune's gravity rather than forming alongside the planet. The eccentricity of Nereid's orbit, coupled with its distant location from Neptune, sets it apart from the more stable orbits of Neptune's other moons. This raises the possibility that Nereid is a relic from the outer reaches of the solar system, perhaps a body from the Kuiper belt or beyond, which was pulled into Neptune's gravitational field at some point during the early history of the solar system. The eccentric nature of Nereid's orbit also suggests that it may have had a close encounter with Neptune in the past, or that Neptune's migration through the solar system may have played a role in capturing it. Some scientists even speculate that Nereid could have been part of a larger body that broke apart, with fragments being scattered into different orbits. The complexity of Nereid's orbit challenges our understanding of the gravitational dynamics at play, as it is not easy to explain how such a distant and eccentric moon came to be in its current position. While the smaller moons of Neptune like Nereid are intriguing, they also provide an essential context for understanding the larger moons and planetary systems. The capture of Nereid and its highly eccentric orbit could be linked to the ongoing processes of planetary migration, an idea that is gaining traction among planetary scientists. It's possible that Neptune's orbit was not always where it is today, and that the planet may have moved inward or outward during its early history, capturing moons like Nereid along the way. In the broader context of the solar system, moons like Himalia, Hyperion, and Nereid provide a contrast to the major moons of the gas giants. These smaller, more distant moons may not have the same level of attention or focus as the large, active moons like Titan or Europa, but their very existence poses questions about the origins and evolution of our solar system. These moons offer us a different perspective on how moons form, how they are captured by the gravitational pull of their parent planets, and how they evolve over time. The continued study of these forgotten moons is essential for piecing together the larger narrative of the solar system's formation. Every moon, whether large or small, regular or chaotic, plays a role in shaping our understanding of the cosmos. By examining the less explored moons of Jupiter, Saturn, and Neptune, we not only learn about their individual histories but also gain insight into the broader processes that have shaped the entire solar system. These moons are windows into the past, a reminder that the story of the solar system is far more complex and diverse than we might think. As future missions, perhaps with advanced probes, telescopes, or even landers, make their way toward these enigmatic moons, we may discover even more surprises. Moons like Himalia, Hyperion, and Nereid could one day be at the center of groundbreaking discoveries, revealing hidden secrets about the early solar system, the formation of planetary systems, and the dynamic processes that continue to shape our corner of the cosmos. The forgotten moons are anything but forgotten. They are the unsung heroes of our understanding of the solar system, reminding us that the answers to the most profound questions are often hidden in the most unexpected places. The forgotten moons, like Himalia, Hyperion, and Nereid, often go unnoticed in the grand narrative of the solar system. But their intricate orbits, unique characteristics, and mysterious origins give them an undeniable significance in the ongoing quest to understand the cosmos. The study of these moons is not just an exploration of individual objects, but a step toward unlocking the secrets of how our solar system, indeed even other planetary systems, came to be. By studying moons such as these, scientists gain insight into planetary migration, gravitational interactions, and the processes that shape celestial bodies in ways that large moons like Europa or Titan cannot reveal. Their eccentric orbits and irregular shapes provide clues to the turbulent history of the solar system, suggesting that the environment of the early solar system was far more chaotic and dynamic than we previously imagined. While moons like Europa and Titan captivate us with their potential to harbor life, moons like Himalia, Hyperion, and Nereid offer a more complex and nuanced picture of the solar system's evolutionary story. The gravitational interactions between planets and their moons are far from simple. As we continue to explore these moons, we learn more about the gravitational forces that govern their movements, which can offer insight into the formation and evolution of entire planetary systems. For instance, the chaotic orbits of moons like Hyperion and Himalia suggest that their paths were not initially stable but were likely influenced by nearby planetary bodies or other moons. This gravitational dance hints at a more complex history for these moons, one shaped by constant shifting and interactions between multiple forces in the solar system. Himalia's capture by Jupiter, for example, suggests that it was once an object from the outer reaches of the solar system, perhaps from the Kuiper belt or even the Oort cloud. Its unusual orbit and composition reflect the fact that it did not form in situ but was brought to its current location by gravitational forces. This capture theory has significant implications for our understanding of how moons are formed and how they might interact with their parent planets over time. If Himalia did indeed originate far from Jupiter, then its journey to the gas giant's orbit could reveal much about the dynamics of the early solar system, about how objects in the Kuiper belt were scattered inward, or how gas giants like Jupiter could have influenced the motion of distant bodies. Hyperion, with its chaotic rotation and porous surface, tells an equally fascinating story. The moon's surface, marked by large craters and unusual sponge-like features, suggests a history of violent impacts and constant bombardment. But its chaotic rotation, caused by the gravitational tug-of-war between Saturn's moons, is just as important in understanding how moons evolve. Hyperion's spin may not be stable, but this peculiar behavior offers a window into the forces at play in the Saturnian system, forces that were likely present during the early history of the solar system and may have played a role in the evolution of other moons and planetary bodies. Hyperion's complex behavior, driven by the intricate gravitational interactions with Saturn's other moons, suggests that these forces might have been far more influential than previously thought. Similarly, Nereid's highly eccentric orbit around Neptune has provided an opportunity to study the impact of planetary migration on the behavior of distant moons. Nereid's capture by Neptune and its highly elliptical orbit suggests that it did not originate in its current position but was once part of the outer solar system. The dynamics of Neptune's interaction with other bodies, especially with the Kuiper belt, raise intriguing questions about how moons are captured and how planetary systems evolve over time. Nereid's odd orbit challenges our assumptions about the gravitational forces that govern the movements of moons, and by studying it, we learn more about the chaotic processes that could have shaped the solar system in its formative years. The capture of moons like Nereid, Himalia, and Hyperion into their current orbits is a reminder of the chaos that likely characterized the early solar system. Planetary migration, gravitational interactions, and the violent collisions between objects would have been commonplace as the solar system settled into the configuration we observe today. But even now, these moons are not passive relics of the past. Instead, they continue to provide a wealth of information about the forces that shape them and the broader processes that govern the solar system's ongoing evolution. It is not just their orbits and compositions that make these moons fascinating. Their potential for future exploration adds another layer of intrigue. Imagine what we could learn about the early solar system by sending a probe to Himalia, Hyperion, or Nereid. These moons may hold crucial clues about the conditions that existed when the solar system was forming, clues that are locked in their surfaces, their atmospheres, if they have any, and their interactions with their parent planets. While Europa and Titan remain in the spotlight due to their potential for harboring life, moons like Himalia, Hyperion, and Nereid offer equally exciting prospects for scientific discovery. The study of these forgotten moons could not only enhance our understanding of the solar system but also provide valuable insight into the processes of moon formation and the development of planetary systems beyond our own. Moons like Himalia, Hyperion, and Nereid are just as important as their more famous counterparts, and their study could lead to groundbreaking discoveries that reshape our understanding of the cosmos. As technology advances and we develop more sophisticated methods for exploring the outer solar system, moons like these may no longer be forgotten. They may become focal points for future missions that seek to unlock the mysteries of the solar system's early history and the complex forces that continue to shape it. Whether we send probes to capture high-resolution images of their surfaces, analyze their composition, or study their gravitational interactions with nearby moons and planets, the forgotten moons are poised to reveal secrets that could transform our understanding of the solar system. By continuing to study these distant moons, we push the boundaries of our knowledge about the solar system and the universe at large. Each discovery made about these moons contributes to a larger picture of how planetary systems form and evolve, how moons are captured and shaped by gravitational forces, and how the early history of our solar system unfolded. These forgotten moons may be overlooked today, but their time in the spotlight may yet come, and the discoveries they hold will undoubtedly enrich our understanding of the cosmos in ways we have only begun to imagine. In the grand scheme of things, Himalia, Hyperion, and Nereid serve as poignant reminders that there is always more to the story than meets the eye. Even the most obscure, distant objects in the solar system have a role to play in the ongoing exploration of space. As we continue to unravel the mysteries of these forgotten moons, we come one step closer to uncovering the untold history of our solar system. A history that is far richer, more complex, and more mysterious than we could have ever imagined. The forgotten moons of the solar system, Himalia, Hyperion, Nereid, and others, serve as compelling pieces of the cosmic puzzle, offering a deeper and richer understanding of the forces at play in the formation of our solar system. In many ways, these moons are living fossils, offering glimpses into the past and the chaotic processes that took place long before Earth was born. The fact that many of these moons were overlooked for so long, overshadowed by the likes of Europa and Titan, only adds to their intrigue. Perhaps, as we continue to explore these moons, we will uncover not only the secrets of their origins but also the complex interactions that gave rise to planetary systems like our own. Take Himalia, for example. This moon's highly eccentric orbit around Jupiter places it in a category of its own, setting it apart from the more familiar moons of the gas giant. Unlike the larger, more prominent moons, Himalia's orbit is much more erratic, suggesting that it may have been captured by Jupiter's gravitational forces, rather than forming in place. This brings to light the possibility of a much more dynamic and chaotic early solar system. The gravitational tugs between Jupiter and other objects, such as asteroids and comets, would have created a turbulent environment in which moons like Himalia could have been captured and thrown into highly elliptical orbits. Himalia's irregular shape and composition further support the idea that it was not formed in situ. Unlike the spherical shape that results from the self-gravity of large moons, Himalia's elongated, irregular form is a testament to its tumultuous past. It is believed that this moon is made up of a mixture of rock and ice, common among the irregular moons in the outer solar system. This composition suggests that Himalia likely originated in the distant reaches of the solar system before it was brought into Jupiter's orbit. In this sense, Himalia may act as a window into the early solar system, revealing the processes that govern the capture of distant objects and how the solar system's larger planets influenced the trajectories of smaller bodies. Hyperion, on the other hand, stands out due to its peculiar rotation and sponge-like surface. Unlike most moons, which rotate in a predictable manner, Hyperion exhibits a chaotic, irregular spin. This erratic rotation is caused by the complex gravitational interactions with Saturn's other moons. These interactions have destabilized Hyperion's rotation, causing it to tumble through space in a seemingly random fashion. This chaotic behavior offers insight into the forces at play in Saturn's moon system, revealing the intricate gravitational dance between moons and the impact it can have on the rotation and orbital stability of individual bodies. Hyperion's sponge-like surface, with its large, porous craters, further adds to its mystery. Scientists believe that the moon's low density and the peculiar features of its surface may be the result of impacts from comets or asteroids, which would have created the moon's strange and porous texture. These impacts likely occurred over billions of years, shaping Hyperion into the oddball moon that it is today. Nereid, with its highly eccentric orbit around Neptune, provides another fascinating case study in the dynamics of the outer solar system. Nereid's orbit is highly elliptical, making it one of the most eccentric moons in the entire solar system. This odd orbital path suggests that Nereid, like Himalia, was likely captured by Neptune's gravity rather than forming in situ. In fact, some scientists believe that Nereid may have originally been a part of the Kuiper belt or an object from the Oort cloud. Over time, gravitational interactions with Neptune and other bodies in the solar system may have altered Nereid's trajectory, pulling it into its current orbit. The strange orbit of Nereid also raises questions about the broader dynamics of the outer solar system. The gravitational interactions between Neptune and other large objects in the region would have been strong enough to influence the orbits of distant bodies like Nereid. These interactions may have been part of a larger process of planetary migration, in which Neptune and other gas giants slowly migrated inward, pushing smaller objects into different orbits or even capturing them in the process. Nereid's orbit, with its wild eccentricity, offers a glimpse into the violent and chaotic processes that shape the outer reaches of our solar system. The study of moons like Himalia, Hyperion, and Nereid also helps scientists to refine their models of how planetary systems evolve over time. Planetary migration, in which planets move through the solar system and interact with nearby objects, is a process that plays a key role in shaping the orbits and characteristics of moons and smaller bodies. The existence of moons with highly eccentric orbits or unusual features suggests that these moons were not formed in the orbits they currently occupy but were instead influenced by the gravitational interactions of the larger planets. This realization challenges our previous assumptions about how moons form and how they move through space. The exploration of these moons also underscores the importance of looking beyond the well-known moons of the solar system, like Europa and Titan. While these moons are captivating in their own right, particularly because of their potential for harboring life, the study of lesser-known moons like Himalia, Hyperion, and Nereid offers an entirely different set of scientific insights. These moons help us understand the broader processes of moon formation, planetary migration, and gravitational interactions, processes that are fundamental to the formation of all planetary systems, including those around distant stars. In addition to their scientific value, these forgotten moons may one day play a role in the future of space exploration. As technology improves, scientists will have the ability to send probes to these distant moons to study their surfaces, composition, and potential for harboring life. While moons like Europa and Titan may be the primary targets for astrobiological studies, moons like Himalia, Hyperion, and Nereid may hold clues to the conditions that existed in the early solar system. Even if they do not harbor life, these moons could provide insight into the conditions that made Earth, and potentially other planets, capable of supporting life. Their unique characteristics may also reveal important information about the processes that govern the evolution of moons and planets in distant solar systems. The forgotten moons of the solar system, Himalia, Hyperion, Nereid, and others, are far from insignificant. Their irregular orbits, unique features, and complex histories offer valuable insights into the formation and evolution of the solar system. These moons may not have the fame or intrigue of moons like Europa or Titan, but they are no less important in our quest to understand the cosmos. As we continue to explore these distant bodies, we will uncover new secrets about the chaotic processes that shaped our solar system and gain a deeper understanding of the forces that govern the motion of moons, planets, and stars. The forgotten moons may no longer be forgotten, and the discoveries they hold will continue to inspire scientific inquiry for generations to come. As we push the boundaries of space exploration, these forgotten moons offer the promise of new scientific frontiers. The mysteries surrounding Himalia, Hyperion, Nereid, and their peers serve as a reminder that even in a solar system as studied as ours, there is still so much left to discover. With the advancements in technology, missions like NASA's James Webb Space Telescope, the upcoming Europa Clipper, and other planetary exploration probes might one day turn their gaze toward these distant and neglected moons. The outer solar system, often overlooked in favor of the more glamorous inner planets, has become a treasure trove for space scientists. We are beginning to realize that objects like Himalia, Hyperion, and Nereid could be key pieces of the puzzle in understanding the early solar system and the broader mechanics that govern celestial bodies. As each mission unfolds, we will likely uncover more of these moon stories that were once hidden in the vast reaches of space. Take Hyperion's chaotic rotation, for example. The sheer unpredictability of its spin speaks volumes about the gravitational forces at work in the Saturnian system. Hyperion doesn't follow the predictable rules that most moons abide by. Instead, it behaves like a chaotic marionette, with its irregular rotation serving as a testament to the complex gravitational interactions in Saturn's orbit. Scientists are eager to further investigate how these interactions came to be, and how such an unusual motion could help us understand more about the early dynamics of the Saturn system. The fact that Hyperion is part of the Saturn system itself, and its behavior is not an anomaly, hints at the intricate relationships between moons, planets, and other celestial bodies in ways that we are only beginning to comprehend. Then there's Nereid with its orbit that defies expectations. The extreme eccentricity of Nereid's orbit makes it one of the most fascinating moons in our solar system. While many moons have relatively circular orbits, Nereid's orbit is far from the norm. Scientists have long puzzled over how such a wild, elongated orbit could be sustained for billions of years. The most likely explanation is that Nereid was captured by Neptune's gravity after it was deflected by another object, possibly a comet or an asteroid. This orbit may be a remnant of the chaotic period in the early solar system when many objects were pulled into the gravitational influence of the gas giants. Studying Nereid could help scientists understand the larger processes of capture and orbital migration that influence the formation of other moons in the outer solar system. What's even more intriguing about Nereid's orbit is the possibility that it may offer clues about the conditions in the Kuiper belt and beyond. The Kuiper belt is home to a vast array of icy bodies and dwarf planets, and Nereid could have originated there. If that's true, then the study of Nereid's trajectory and orbit could shed light on the early formation of the solar system and the interactions between distant objects that took place billions of years ago. Nereid's unusual orbit could serve as a window into the distant past, providing clues about how objects in the outer solar system were moved and reshaped by the gravitational forces of Neptune and the other gas giants. Then there's the case of Himalia, which, as mentioned before, orbits Jupiter in a highly elliptical path. Himalia's irregular orbit could be evidence of a violent past. In the early solar system, the gravitational influence of Jupiter would have been intense, and objects like Himalia may have been captured by the planet's gravity after being deflected from the asteroid belt. This captures the chaotic nature of the solar system's infancy, where planets were still migrating and objects were being flung into new orbits. Himalia's orbit is a relic of these turbulent times. Its composition also tells a story. It's made up of a mix of rock and ice, which places it in the same category as many other irregular moons that likely originated in the cold outer reaches of the solar system. While Himalia may not be a prime candidate for astrobiological exploration, its story is just as important to understanding the development of our solar system. By studying moons like Himalia, scientists can gather crucial data about the types of objects that existed in the early solar system, the dynamics of Jupiter's gravitational field, and how moons with unusual orbits came to be. Himalia, along with other moons that have similar characteristics, provides an invaluable snapshot of the forces that shaped our cosmic neighborhood. In the coming years, it's likely that we'll be able to study these moons in greater detail. With missions to Jupiter and Saturn, as well as other outer solar system destinations, the forgotten moons are likely to be rediscovered as we learn more about the intricacies of planetary formation. As scientists continue to expand their understanding of the solar system, the mysteries surrounding these moons will come into clearer focus. One day, a mission may land on Himalia, Hyperion, or Nereid, allowing us to study them up close and unlock their secrets. Each of these moons is unique, with its own history and set of characteristics. Himalia's irregular orbit, Hyperion's chaotic rotation, and Nereid's eccentric path all point to a deeper, more complex story of solar system formation. They remind us that the solar system is not a static, well-organized collection of planets and moons, but rather a dynamic and constantly changing environment where objects are constantly being shaped and reshaped by gravity, collisions, and interactions with other celestial bodies. While the famous moons of Jupiter and Saturn, like Europa, Titan, and Ganymede, often capture the imagination of both the public and the scientific community, the forgotten moons offer their own valuable insights. They are the unsung heroes of the solar system, serving as critical clues in the puzzle of how the planets and moons were formed, and they may one day reveal even more about the potential for life elsewhere in the universe. For now, the forgotten moons remain largely unexplored. But as technology advances and our ability to explore the outer solar system grows, we can look forward to new discoveries and a deeper understanding of these enigmatic worlds. They are not just the forgotten moons of the solar system, but key players in the story of our cosmic origins. As our understanding of these forgotten moons deepens, it becomes clear that they are not mere relics of the past. They are pieces of the cosmic puzzle that could revolutionize our understanding of planetary science. While we focus on the larger, more studied moons, We are only beginning to grasp the complexity of the moons that orbit on the periphery. Their orbits, their composition, and their mysterious behaviors all hold valuable information that could transform our knowledge of the early solar system and beyond. Europa, Titan, and the other well-known moons of the gas giants are often the stars of planetary exploration, and rightfully so. Europa's potential subsurface ocean and Titan's atmosphere have made them prime candidates for astrobiological studies. However, this should not diminish the importance of moons like Himalia, Hyperion, and Nereid. These moons may lack the immediately exciting features that make Europa or Titan stand out, but their subtle quirks and peculiarities hold a unique allure for scientists. They present opportunities for discoveries that could shift the very foundation of how we view our solar system. One of the fundamental lessons we can learn from the forgotten moons is the nature of planetary system formation. The moons that orbit gas giants like Jupiter and Saturn were not always in the stable orbits they occupy today. Early in the history of the solar system, the gas giants were still migrating through the chaotic debris field of the young solar system. During this time, moons like Himalia and Hyperion may have been captured, deflected, or even formed from collisions between larger objects. The intricate dance of gravitational forces between Jupiter, Saturn, their moons, and the many objects of the Kuiper belt and asteroid belt shape their orbits in ways that defy easy explanation. For example, the peculiar orbit of Hyperion has been a source of fascination. Its strange, chaotic rotation suggests that it has been influenced by a variety of forces over time. Some scientists believe that Hyperion was once part of a larger body that broke apart, and the resulting fragments were scattered in ways that altered the moon's original trajectory. Others think that Hyperion's orbit could be the result of gravitational interactions with Saturn's other moons or even a cometary impact that disrupted its original motion. This chaotic behavior challenges scientists to rethink how gravitational forces operate in the outer solar system and what factors contributed to the irregular behavior of moons like Hyperion. Nereid's orbit, on the other hand, provides us with another fascinating puzzle. Its highly eccentric orbit, which ranges from nearly 1.35 million kilometers to about 9.6 million kilometers from Neptune, suggests that Nereid was not always in its current path. Many researchers believe that Nereid may have originally been captured by Neptune's gravity, possibly after being deflected by another object. This hypothesis points to a period in the early solar system when the gravitational interactions between Neptune and other objects were much more chaotic. The extreme nature of Nereid's orbit could be the key to understanding how distant moons and comets were captured by the gas giants during the tumultuous birth of the solar system. The composition of these moons also offers important insights into their origin. Himalia, for instance, is primarily composed of rock and ice, a feature that is common among irregular moons. This composition suggests that Himalia may have been captured from the asteroid belt or formed as part of a larger object that broke apart. Similarly, Hyperion's porous structure hints at the possibility of it being a fragment of a larger body that was shattered during the early chaotic period of solar system formation. These moons could be remnants of objects that existed in the outer solar system but were broken apart or scattered by gravitational interactions with the gas giants. Their study could provide critical evidence about the processes that shaped the early solar system and offer clues about the composition of objects in the Kuiper belt and beyond. In addition to their value in understanding solar system formation, the forgotten moons also present a fascinating opportunity for future exploration. While they may not have the same immediate appeal as Titan or Europa, these moons are prime candidates for future missions aimed at unlocking the secrets of the outer solar system. Missions that explore moons like Himalia, Hyperion, and Nereid could provide us with a deeper understanding of their origins, their current behavior, and their role in the solar system's history. Given the technological advances in space exploration, we are now capable of conducting detailed studies of these moons, and it is only a matter of time before they become the focus of future missions. As we look ahead to the next generation of space exploration, the forgotten moons of the solar system may play a crucial role in expanding our understanding of the universe. Space telescopes like the James Webb Space Telescope and future missions like NASA's Europa Clipper may provide us with detailed images and data that reveal the hidden wonders of moons like Himalia, Hyperion, and Nereid. These moons may not be the most glamorous or well-known, but they offer unique insights into the formation and evolution of the solar system. Their unusual orbits, eccentric behaviors, and diverse compositions make them invaluable to our study of planetary science. For now, these moons remain largely in the shadows, their mysteries waiting to be uncovered. But with each new discovery, we are slowly piecing together a more complete picture of the solar system and its history. The forgotten moons may not be the first objects that come to mind when we think of space exploration, but their stories are just as important as those of the more famous moons and planets. As we continue to explore the outer reaches of our solar system, we will undoubtedly uncover more secrets about these fascinating and enigmatic worlds. The forgotten moons remind us that there is still so much to learn about the solar system. With each new mission, each new discovery, we gain a deeper understanding of the forces that shaped our cosmic neighborhood and the potential for new worlds yet to be discovered. Himalia, Hyperion, Nereid, and their peers are the unsung heroes of the solar system, waiting for their time in the spotlight. And when that time comes, they will reveal secrets that could reshape our understanding of the solar system and our place in the cosmos. As we continue to explore the outer reaches of the solar system, we begin to realize just how much we still don't know. The forgotten moons are just one aspect of this vast, uncharted territory, a reminder of the complexity and mystery that surrounds our cosmic neighborhood. These moons, once overlooked, hold the potential for discoveries that could radically alter our perception of space, time, and the evolution of planetary systems. As technology advances, the possibility of sending missions to study these enigmatic moons becomes more feasible, and with it, the hope that we can uncover secrets that have been hidden for billions of years. One of the most intriguing aspects of moons like Himalia, Hyperion, and Nereid is how their irregularities in shape, orbit, and composition suggest they may not have always been where they are now. For example, Hyperion's chaotic rotation is not only a curiosity from an engineering perspective, it could also be a clue to the violent and tumultuous early days of the solar system. The irregularities in Hyperion's spin suggest that it may have been subjected to significant impacts and gravitational interactions with nearby objects. This kind of behavior could help scientists understand the types of collisions and encounters that occurred in the early solar system, providing insight into the environment in which the gas giants formed. In addition to the irregular behavior of moons like Hyperion, Nereid's eccentric orbit around Neptune presents a fascinating puzzle. The orbital eccentricity of Nereid is so extreme that it has led scientists to consider a range of possible scenarios for its origin. Some believe that Nereid was once part of a larger, more stable system, but was deflected into its current orbit due to a gravitational interaction with Neptune or another celestial body. Others speculate that it could have been captured from the Kuiper Belt, an icy region beyond Neptune. In either case, Nereid's unusual orbit challenges our understanding of how moons are captured and maintained in the gravitational grip of their parent planets. These moons, while not receiving the same level of attention as their more famous counterparts, are key to unlocking the mysteries of the outer solar system. The gas giants, with their complex systems of moons, have long been a source of fascination for astronomers and planetary scientists. But it is in the study of these lesser-known moons that we may find the most revealing clues about the formation of the solar system and the processes that govern planetary dynamics. The discovery of Himalia, Hyperion, Nereid, and other forgotten moons may be the beginning of a new era in planetary exploration. While Europa and Titan have captured our imagination with their potential for hosting life and their intriguing surface features, these forgotten moons could offer a wealth of information about the early solar system and the forces that shaped its evolution. Their study could provide answers to some of the most fundamental questions about the nature of moons, the processes that govern their orbits, and the way in which planetary systems form and evolve over time. One of the biggest challenges in studying these moons is the sheer distance and difficulty in reaching them. Himalia, for instance, orbits Jupiter at a distance of approximately 11 million kilometers. While this may seem relatively close in the context of the vastness of the solar system, it still presents significant challenges for spacecraft attempting to reach it. Hyperion, on the other hand, orbit Saturn at a distance of roughly 1.5 million kilometers, which is considerably closer but still presents considerable logistical challenges for exploration. Despite these obstacles, missions to these moons could provide some of the most exciting discoveries in planetary science. Currently, missions like NASA's Juno spacecraft, which is studying Jupiter's atmosphere and magnetosphere, provide valuable data on Jupiter's moons, including Himalia. However, in-depth exploration of these moons will require dedicated missions, potentially including landers, orbiters, or even sample return missions that could bring back material from the moon's surfaces for analysis. These kinds of missions would offer insights into the composition of these moons and provide clues about their histories. Future spacecraft could also employ new technologies, such as advanced ion propulsion systems, which could help reduce travel time and improve our ability to reach these distant moons. In the meantime, our understanding of these moons is being shaped by remote observations made using telescopes and space-based observatories. These observations have provided invaluable information about the size, shape, and composition of these moons. For example, the Hubble Space Telescope has captured detailed images of Hyperion, revealing its irregular shape and porous surface. Similarly, observations from the Keck Observatory and other ground-based telescopes have provided insights into the orbits and gravitational interactions of moons like Nereid. One of the most exciting aspects of studying these forgotten moons is their potential to offer clues about the early solar system. These moons, with their strange orbits and unique compositions, may hold the key to understanding the processes that govern the formation of the planets and their satellites. For instance, the irregularities in the orbits of moons like Nereid and Hyperion suggest that they may have been captured or deflected by gravitational interactions with larger bodies. This could provide valuable information about the chaotic nature of the early solar system, when objects were constantly colliding, merging, and being deflected by the gravity of larger planets. The study of these moons could also shed light on the processes that led to the formation of the gas giants themselves. The gas giants, including Jupiter and Saturn, are thought to have formed from the accumulation of gas and dust in the early solar system. However, the exact details of their formation are still a matter of debate. By studying the moons that orbit these giants, scientists can gain insights into the conditions that existed in the early solar system and how these conditions may have influenced the formation of the planets and their satellites. The study of forgotten moons like Himalia, Hyperion, and Nereid could be instrumental in unlocking the secrets of planetary formation and the history of our solar system. As we look toward the future, the forgotten moons of the solar system offer an exciting frontier for exploration. While these moons may not be the most glamorous or well-known, their unusual characteristics make them fascinating subjects of study. As our technology improves and our ability to explore the outer solar system advances, these moons may reveal secrets that have been hidden for billions of years. Whether it's the chaotic spin of Hyperion, the eccentric orbit of Nereid, or the icy surface of Himalia, each of these moons has a story to tell. And as we continue to explore the mysteries of the solar system, we may find that these forgotten moons hold the answers to some of the most fundamental questions about the nature of our cosmic neighborhood. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.